It began like any other quiet stretch on the calendar, until it did not. In the span of a few days, the planet served up two headlines that seemed to belong to different genres entirely. First, a powerful earthquake shook one of the most volatile arcs along the Pacific Rim, the kind of rupture you feel in your bones, even from far away because the maps light up and the ocean sensors start paying attention. Then, not long before or after, depending on where you were standing, Earth's magnetic shield rang with a strong geomagnetic storm. The sky glowed far from the poles, radio operators grumbled about static, and engineers watched their monitors the way pilots scan a crowded runway. It was a double shock, one deep underfoot, one draped across the sky. When events like this arrive in close succession, our pattern-hungry minds do the rest. We draw a line between them. We ask if the sun whispered to the faults. We wonder if the timing is more than coincidence. That question is the engine of this film. Not because we plan to force an answer, but because following the question takes us somewhere useful. It takes us into the machinery of earthquakes and into the physics of space weather. It shows us what we truly know, what remains debated, and what is still only an intriguing possibility. If you have ever watched the aurora, you have seen the upper atmosphere respond to streams of charged particles from the sunday. If you have ever seen a seismogram march across a screen after a big rupture, you have watched the crust release decades of stored stress in minutes. These are not vague forces. They are measurable. The solar wind is clocked in kilometers per second. Magnetic disturbances are logged in indices that spike when the field wobbles. Seismic energy is counted on a magnitude scale that has nothing to do with how it feels in your living room and everything to do with how much the fault moved and how far. Two systems, both noisy, both regular, both able to surprise. Here is the first anchor we need. The consensus view in seismology holds that earthquakes are the result of tectonic stress building up on faults until friction can no longer hold. The trigger that sets the exact minute is often small compared to the forces that loaded the fault. Tides can change stress by a hair. Seasonal rain and snow can change the weight on the crust by a hair. Extraction, or injection of fluids, can change pressure in rock by a hair. Small does not mean irrelevant. It means timing matters only when the system is already close to failure. That idea will travel with us throughout this story. Here is the second anchor. Space weather is real in the most practical sense. It bends compass needles. It knocks satellites into safe modes. It flows as currents on long wires that we bury in the ground and string across continents. During a strong storm, the ionosphere swells and ripples, which matters if you depend on precise timing and navigation signals. None of that needs drama to be interesting. It is already a powerful part of modern life. So why does the weekend feel impossible to some people? Because when you look at the timeline, the quake and the storm sit near each other like two suspicious strangers on a train. Correlation is seductive. It is also a trap. The right question is not did one cause the other. The right question is whether there is any plausible pathway by which changes in the electromagnetic environment could shift conditions along a fault that was already close to letting go. The answer may still be no. If it is no, that is honest progress. If the answer is maybe under very specific circumstances, that also matters. It means we can write down those circumstances and test them the next time the sun throws a tantrum. Before we chase possibilities, we draw a boundary. We will keep the facts that are plain. A major earthquake happened along a known subduction zone. A strong geomagnetic storm happened when high-speed solar wind swept past our planet. These are the knowns. We will keep the methods that are plain. You, at home, can verify both with public data sets. The rest of the film will translate that data into pictures and questions that make sense without turning you into a specialist. This is not a story about fear. It is a story about scale. Tectonic stress is measured in units that dwarf any push from weather or human habit, yet tiny nudges can choose the hour when a loaded fault finally slides. Solar wind energy is vast when spread across the planet, yet the deep crust is stubborn and heavy. Where these realities meet is a narrow doorway. If there is any connection, it likely lives in that doorway, not in wild claims about the sun commanding earthquakes. Our promise is simple. We will move fast, but we will not cut corners. We will keep a clean line between what has been demonstrated, what is debated among experts, and what sits in the realm of open speculation. You will hear some careful phrases. One possibility, island. A competing view suggests it remains uncertain whether. Evidence is limited, but one inference, island, a minority view, holds that. Those signals are not hedges, they are the handles we use to carry complex ideas without dropping them. There is also wonder here. An interstellar visitor has wandered into our yard. Several comets are writing faint calligraphy across the solar wind. The sun is restless. The planet below is busy resetting its stress map after a giant release. It is a moment when the known and the unknown sit at the same table. That is when science is at its best, not to provide a final verdict, but to show us how to ask better questions and how to check our answers. So we begin where the weekend left us. With a deep breath, with a map that shows the fault where rock slipped, with a map that shows the aurora, where the sky answered the Sunday, with a single question placed between them like a bridge. Could space weather nudge a fault that is already near failure? To chase that, we need to understand what earthquakes are, and just as importantly, what they are not. We also need a tour through the storm you cannot touch. The tour starts now. Our through line is this. Hold the facts tight, chase the mystery with curiosity, and do not mistake drama for proof. Next, we will step onto firm ground and let seismology speak first. Then, we will climb into the wind that never stops. Between these worlds lies the real story of that impossible feeling, and whether it is earned or just a trick of timing. Before we ask whether the sky can whisper to the ground, we need to let the ground speak clearly. Seismology is a mature science. It does not know everything, but it knows the basics of why the crust breaks and when patterns are expected to follow. The picture starts with plates that move slowly on a hot interior, and with faults that are scars, where blocks of rock slide past, dive beneath, or collide. Motion loads these faults with stress over years to centuries. Friction holds them until it does not. When strength is exceeded, the fault slips, the rock rebounds, and elastic energy radiates as seismic waves. That is an earthquake. The magnitude scale is a measure of energy release, not a measure of fear. Each whole number step on the moment, magnitude scale represents roughly 32 times more energy. A magnitude 6 is not a slightly bigger version of a 5. It is a different class of event. This simple fact explains why large earthquakes dominate how a region resets its stress. Many small quakes still matter because they outline active structures and because they tell us the crust is alive, but they are not substitutes for a single great rupture. After a large rupture, the ground does not simply relax and go quiet. It rearranges its stress field. Some nearby patches of the fault become safer for a time. Others become more likely to fail. This redistribution is captured by Coulomb stress change, a calculation that estimates which areas were brought closer to failure based on how the main shock changed the stress directions. The results often match where aftershocks cluster. This is not magic, it is mechanics. When a giant segment slips, neighbors feel it. Some are pushed, some are pulled. Aftershocks are not random noise. They follow patterns that have been observed in sequences across the world. The Amori law describes how the rate of aftershocks decays with time. The decay is steep at first, and then slows in a long tail. The Gutenberg-Richter relation describes the ratio of small to large events in a region. Put together, these two ideas help seismologists say what counts as normal activity after a main shock. They do not predict any one event to the minute, but they set expectations for clusters, sizes, and time decay. Triggers sit on top of this loaded system. They are small pushes that can advance or delay the moment a fault that is already close to failure finally slips. Earth tides from the pull of the moon, and the sun barely change stress. But in some volcanic areas, and on some faults that are critically stressed, the tide can modulate microseismicity. Changes in air pressure can nudge shallow faults very slightly. Heavy rain or snow can change the weight on the crust, and can change pore pressure in shallow layers. Human activity can also act as a trigger. Injection of fluids into deep formations can raise pore pressure along a fault and lower its effective friction. Extraction of groundwater can change stress fields. Reservoir filling can load a fault. These examples do not create tectonic stress. They are timing agents, acting on a system that is already primed. Scale matters. The stresses that build on major plate boundary faults are measured in units far larger than the perturbations caused by weather or normal human life. That is why most days pass without any effect from the countless small changes above our heads. It is also why researchers are careful with language. A trigger is not a root cause. When a fault goes, the energy was stored over geologic time. The trigger, if any, only chose the hour. Now to what earthquakes are not, according to the mainstream field, they are not reliably forecast by single precursors. Many signals have been proposed, from unusual animal behavior to lights in the sky to electromagnetic blips. Some can be traced to real physical processes. Rock cracking under high stress can produce weak electromagnetic signals in the lab. Gas releases can affect local air conductivity. These are interesting observations, yet they have not delivered a consistent and useful prediction method at regional scales. Agencies that keep public safety as their mission continue to say that short-term prediction is not possible with current science. What is possible is hazard assessment. We can map where the risk is high based on geology and past behavior. We can build codes and plans accordingly. Space weather belongs in that same careful frame. Geomagnetic storms are known to induce currents in long conductors on the surface. They can disrupt navigation and communications. The consensus in seismology, however, is that there is no demonstrated causal link between magnetic storms and the generation of tectonic earthquakes. Statistical studies that claim associations often struggle with selection effects, and with the fact that both earthquake catalogues and geomagnetic indices are rich with variability. When you compare two noisy signals after the fact, it is easy to find patterns that fade when you change the window or the region. None of this means that testing ideas is pointless. It means the bar for evidence is high. A testable claim would specify which solar wind conditions matter, how large a change in stress inside the crust is plausible, what time window should show the effect, and how the result differs from normal aftershock decay. It would also require pre-committed criteria before the next storm arrives. That is, how you protect yourself from the seduction of hindsight. If you want to see the knowns for yourself, you can. Earthquake catalogues from national agencies are updated in near real time. They list location, depth, magnitude, and focal mechanism. Space weather dashboards show solar wind speed, density, and magnetic field measurements from satellites that sit upstream of Earth. Look at both, and the first lesson is humility. The planet is active all the time. The sun is busy all the time. Overlap is guaranteed somewhere on most days, simply because both systems never sleep. Seismology carries one more lesson that matters for the rest of this story. Great earthquakes change the odds for weeks to years in the surrounding region. That alone can explain a second large event nearby, without invoking anything from beyond the atmosphere. When we later evaluate timing, we must hold that baseline firmly in view. Otherwise, we risk attributing to the sky what the crust can explain on its own. Our through line continues. Ground the narrative in what the field accepts, then test the edges with care. With the mechanics of rupture and aftershock patterns in place, we can now climb into the upper atmosphere and watch how the solar wind presses on the planet. Only after both pictures are clear can we ask, with any honesty, if they touch. Every 11 years or so, the magnetic personality of the sun flips. That reversal is not a simple on-off switch. It is a full season change in a star. Sunspots multiply and fade in long waves. Giant loops of magnetized plasma arch and snap. The solar wind thickens and thins as streams of particles take different lanes through the inner solar system. Earth lives inside that weather. We cannot feel it on our skin, but our magnetic shield feels every gust. The driver is magnetism shaped by boiling plasma. The sun is a sphere of ionized gas. Motion in that gas acts like a dynamo and builds fields that twist and braid. When the field is tangled, more active regions appear on the visible surface. These are the dark sunspots you see in photographs, cooler than their surroundings because the field lines there bottle heat and slow the churn. Active regions are the staging grounds for energetic outbursts. They are the storm factories. Two kinds of solar disturbances matter most for us. One is the coronal mass ejection. That is when magnetic structures in the outer atmosphere rearrange suddenly and throw a balloon of plasma into space. If that cloud is aimed near our orbit and the embedded magnetic field points the wrong way when it arrives, Earth's magnetosphere can be squeezed and stirred into a strong geomagnetic storm. The other is the high-speed stream that flows from coronal holes. A coronal hole is a place where magnetic field lines open out into space. That open geometry lets the solar wind escape faster than usual for days at a time. High-speed streams create recurrent disturbances. They can produce storms that are less explosive than a direct hit from a mass ejection, but they can last longer. Think of Earth's magnetosphere as a windsock made of invisible field lines. The solar wind pushes on it continuously. When conditions upstream change, the shape and currents inside the windsock change too. Satellites just outside the shield measure the speed of the wind, its density, and the direction of the interplanetary magnetic field. Those numbers tell operators on the ground how much energy is likely to couple into the system. A southward pointing field couples more strongly. It lets energy and particles leak in, the way a door latch lines up and clicks. Inside the magnetosphere, the energy travels along complicated pathways. Some of it accelerates electrons that then race around the planet. Some of it flows along field lines and dumps into the upper atmosphere near the poles. There it lights the sky with aurora, green and red curtains that are beautiful from the ground and full of information for scientists. Part of the energy goes into electric fields that stretch across the polar regions. These fields drive currents in the ionosphere, which is the electrically active layer at the edge of space. The ionosphere is not a static shell. It breathes. It swells in daylight and shrinks at night. It ripples during storms. Those changes matter because radio waves bounce and bend through that layer. Navigation and communications depend on a predictable ionosphere. During strong disturbances, predictability fades. Farther down, long networks act like antennas. Power lines and pipelines can pick up geomagnetically induced currents. These are slow electric drifts, created when the magnetic field above us changes quickly. The induced currents can heat transformer cores and corrode metal over time. Utility operators have learned to watch space weather the way coastal towns watch tide tables. Most storms pass with little trouble. A few demand attention. The solar cycle sets the rhythm for all of this. During quiet years, the wind is often slower and the sun shows fewer spots. The magnetosphere still sputters and dances, but the moves are gentler. During active years, hot regions on the sun and open field lanes appear more often. The mix of fast streams and ejected clouds becomes richer. The storms are more frequent and sometimes stronger. The cycle is not perfectly clockwork, but the broad shape repeats. It is enough to plan around. Our understanding of these processes has grown because we now sample the sun and the inner heliosphere with dedicated missions. One spacecraft skims through the outer atmosphere of the sun and measures the wind almost at the source. Another maps the magnetic environment from a different vantage. Together with older observatories that watch the surface and the corona, they let researchers connect a bright knot on the sun to a change in wind conditions that a satellite near Earth will see days later. That chain of custody, from source to impact, turns space weather into something we can forecast, not with perfect accuracy, but with useful lead time. The indices you sometimes hear about are simply ways to summarize the storm. Some track how disturbed the global magnetic field island. Others track how intense the auroral currents are. They rise when the magnetosphere is loaded and working hard. They fall when the energy dissipates. None of these numbers tells a full story by itself. Together, they sketch the pulse of the system so that pilots, grid operators, and satellite teams can decide whether to change procedures. This is where the known meets the unknown for our film. We know that the sun drives electrical activity in the space around our planet. We know the mechanisms that connect an upstream change in field direction to a glow in the sky and to a spike in a transformer monitor. We do not have to assert anything exotic to be impressed. The chain is remarkable, even in its ordinary form. What remains open for investigation is whether any of this energy couples through shallow or deep pathways into the crust in ways that matter for faults that are already close to failure. That question is subtle because scale is the gatekeeper. The power involved in space weather is large when spread across a continent, yet the stress that locks rock underground is even larger, and much of the crust is a poor electrical conductor. So the sun reawakens with its usual mix of long-lived streams and sudden eruptions. The magnetosphere braces, flexes, and recovers. The sky paints itself in quiet electric colors. The electrical grid hums and keeps the lights on. In the background, instruments log every fluctuation. That record will be our map. We will use it to place the storm and the quake on the same timeline. Then we will ask whether anything beyond a trick of timing is hiding in the overlap. Stand outside on a calm night, and you feel nothing moving in the air. Above you, something is roaring past at hundreds of kilometers per second. That river is the solar wind. It is a thin soup of electrons and ions that streams outward from the sun in all directions. You cannot feel it because Earth wears a cloak. That cloak is our magnetic field, which deflects most of the flow and guides the rest into complex paths. Understanding those paths is the key to understanding how a space storm works. The solar wind is not uniform. Imagine lanes on a highway where one lane carries slow traffic and another carries fast traffic. The slow lane often comes from closed magnetic regions above the solar surface. The fast lane flows from open magnetic regions that let plasma escape more freely. When fast wind catches slow wind, a compression region forms. In that region, density and magnetic field strength can increase. Spacecraft that sit sunward of Earth taste these changes long before the magnetosphere does. Their readings tell us what kind of punch is coming. When the wind arrives at Earth, it meets the magnetic field that rises from the core and expands into space. The dayside boundary is called the magnetopause. It is like the bow wave of a ship. The solar wind cannot easily cross it head-on, so it diverts around. The magnetic field in the wind carries its own direction, which scientists call the interplanetary magnetic field. If that direction points southward relative to Earth's field, magnetic reconnection can occur at the dayside boundary. Reconnection is a process where magnetic lines from different regions break and join, allowing energy and plasma to pass into the magnetosphere more efficiently. Think of two zippers that catch and suddenly open a route. Energy that enters this way does not stay put. The magnetosphere stores it in a region on the night side called the magnetotail. The tail stretches away from the sun like a windsock. Under sustained driving, the tail thins until it reconnects as well. Then, energy is released back toward Earth along field lines. Particles are accelerated and guided into the upper atmosphere near the poles. Collisions with atoms and molecules there produce light. That light is the aurora. It is a beautiful signature of a large-scale electrical circuit that closes through space and through the ionosphere. The ionosphere is a layer of the upper atmosphere that is partly ionized by sunlight. During a storm, it becomes a busy highway for currents. Electric fields appear across polar regions and mid-latitudes. Charged particles drift under those fields. Currents close through the resistive atmosphere. These ionospheric currents are not the only actors. There are also ring current particles that encircle the planet and change the overall magnetic field for hours to days. There are radiation belt electrons that can be energized to astonishing speeds and that threaten satellites. A storm is not a single event. It is an orchestra with many sections, each playing its part on its own tempo. How does any of this touch the ground? The magnetic field at the surface changes when currents above change. According to Faraday's law, a changing magnetic field induces an electric field. Long conductors at the surface can pick up that field. Power lines, undersea cables, and pipelines act as antennas. Slow variations in the magnetic field create slow but persistent geomagnetically induced currents. Those currents can enter transformers and push them toward heating. They can flow through pipelines and accelerate corrosion. None of this requires speculation. Utilities and operators watch it happen, and they prepare for it when forecasts say a strong storm is on the way. The crust beneath those networks is different. It is made of rock that varies in conductivity from place to place. Some regions are more resistive. Others contain fluids and minerals that carry current better. In principle, induced electric fields can thread through the ground and along those conductive paths. In practice, the deep crust is often a poor conductor compared to the ionosphere and the surface networks we have built. That is why most of the storm's energy stays in space or in the upper atmosphere. It is also why direct links from a space storm to a deep fault remain an open question that must be tested with care. If you want a simple mental model, use this. The sun pushes. The magnetosphere catches and stores. The ionosphere glows and carries current. The ground responds weakly, unless you give it a long metal wire or a buried pipeline, which then becomes a helpful unintended antenna. That model explains most of the practical trouble that storms cause, and it explains most of the lights in the sky. It also sets the stage for a fair test of more subtle ideas. If there is any additional pathway, It would likely involve induced fields, finding natural conductors that reach fault zones, or it would involve changes in atmospheric and ionospheric conditions, altering the global electric circuit in ways that slightly change stresses near the surface. Those are research topics, not settled conclusions. Measurements make this invisible storm visible. Upstream satellites report solar wind speed, density, and field direction. Ground magnetometers record how the field varies minute by minute. All sky cameras capture aurora. GPS receivers report how signals bend through the changing ionosphere. When these data streams line up, you can watch a storm build, couple, and relax. A strong southward field arrives. Ground stations see the field swing. Auroras brighten. Indices rise. Over hours, the system dumps energy and returns toward quiet. There is grace in this cycle. The planet and the star engage in a slow conversation that has been going on for billions of years. Life arose under this shield. Our technologies have woven themselves into the same space. The sun will continue to send gusts. The magnetosphere will continue to flex. We will continue to listen. The more clearly we see each road that particles travel, the harder it becomes to smuggle in claims that bypass the known routes. That clarity is our safeguard and our guide. Our through line returns. We now hold a working map of the storm you cannot touch. Next, we return to the ground to examine tiny triggers and the small push problem. Only then can we place both pictures on a single timeline and ask the question that brought us here with any chance of learning something real. This is the hinge of the story. If earthquakes are primed by slow tectonic loading, and if many tiny agents can tilt the timing once a fault is near its limit, then it is natural to ask whether a storm in space could count among those agents. The question does not claim a verdict. It asks about plausibility and about scale. It asks whether any route exists for energy and fields from above to alter conditions inside rocks that are already stressed to the edge. The answer will have to pass through mechanism, through magnitude, and through tests that do not reward coincidences after the fact. Begin with the small push problem. Many observations support the idea that very small stress changes can advance or delay the clock on a loaded fault by minutes or days. Tides change stresses by only a sliver, yet in some places they modulate the rate of tiny quakes. Seasonal snow and rain can add or subtract weight on the crust and can change fluid pressures in shallow layers. Reservoir filling and groundwater pumping show that modest changes in pressure can move faults that are sensitive. None of these examples provides large energy. They provide timing cues to systems that are perched on a ledge. That is why the idea of a space weather nudge is not absurd on its face. It still has to clear the bar of realism. A fair path begins with induced electric fields. During geomagnetic disturbances, the magnetic field above us changes quickly. By Faraday's law, that change induces electric fields at the surface. Long conductors like power lines gladly collect those fields. Rock does not collect them gladly, yet the ground is not uniform. Some formations are resistive, others are laced with brines and clays that conduct more easily. One possibility is that induced fields thread along these natural wires and create local currents in and around fault zones. Currents in a porous medium can change the way ions line up along grain boundaries. That can change effective friction slightly. If pore fluids are present, small electric fields can also influence electrokinetic effects that move charges and pressure at a microscopic scale. The effect would be tiny in most places. It could matter only where the fault is already almost ready to go. A related route involves the global electric circuit. The planet and the ionosphere are coupled through a weak but persistent current system that responds to thunderstorms and to the state of the upper atmosphere. One competing view suggests that geomagnetic storms can modify this circuit by changing ionospheric conductivity over large regions. That in turn could change fair weather fields near the surface. The surface field is small compared to anything in a laboratory. Evidence is limited, but one inference is that long-lived changes in this background field might weakly influence the movement of charges and fluids in shallow rocks. If the target fault is shallow, and if it is near failure, even a subtle change might shift the hour hand without touching the minute hand of larger tectonic stress. There is also the direct current path inside the crust. A minority view holds that strong geomagnetic activity can drive significant currents through deep conductors, and that those currents can heat or chemically alter weak layers. The scale arguments weigh against this in most settings. The deep crust tends to be a poor conductor, and the power available per unit volume is small when spread through large rock masses. Yet geological provinces differ. Some contain long conductive belts left by ancient tectonics. In such places, the induced fields might find easy routes. If that is true, any effect would be geographically selective. That prediction helps with testing because it breaks the idea into regional expectations rather than global claims. Mechanism is only one gate. Magnitude is the next. Seismology speaks in units of stress change that matter for failure. Tectonic loading accumulates stresses that are orders of magnitude larger than the tiny triggers we are discussing. For space weather to matter at all, it would not need to match tectonic energy. It would need to produce changes at the level that tides or fluid pressure can produce in sensitive zones. That sets a target range that is small but not mystical. It also sets a discipline. If an effect exists, it should be strongest in times and places where the induced fields are largest, where conductivity structures connect the surface to depth, and where the fault is already active from local causes. It should also show up statistically as a small timing preference, not as brand new earthquakes in quiet places. With these filters, we can now phrase the core hypothesis in a way that can be wrong. Space weather does not create earthquakes. At most, it advances the clock on faults that have already been loaded to near failure. It does so through weak electrical pathways that alter pore pressures or friction in shallow to mid-crustal rocks. The effect is small and selective. It appears during specific magnetic conditions and in regions with suitable geology. This is a claim that lives or dies on data. It also invites a control. Many strong storms should show no effect in many places, and many earthquakes should occur without any helpful storm nearby. If that is what we find, the honest conclusion is that timing coincidences are exactly that. Skepticism is not a mood in this context. It is a measurement rule. We should demand that any proposed links survive when the next storm arrives, not only when we look backward after. An earthquake captures our attention. We should ask for pre-committed windows, for specific indices, and for geology-based masks that decide in advance where any effect should be strongest. The result can then be scored against a baseline defined by aftershock decay and by the expected rate of events in the region. That kind of scoring does not flatter stories, it tests them. The reward for doing this carefully is clarity either way. If there is no effect, then we retire the idea and keep our wonder focused on the true chain that links the sun to aurora and to transformer alarms. If there is a small effect under special conditions, then we have learned something about how subtle processes can tip systems that are near critical points. That knowledge does not change the fundamentals of hazard, but it adds nuance to how we read noisy timelines when the sky and the ground both seem loud at the same time. Our through line stays steady. Hold the facts tight. Let curiosity explore only along paths that physics can support. Next, we build the testing frame. We need baselines and controls, and a way to compare storms with seismic activity without being fooled by overlap that is guaranteed in a busy planet under a busy star. A fair test starts before the next headline. It begins with a plan written in calm hours, not in the glare of a dramatic week. If we want to know whether space weather can nudge faults that are already close to failure, then we need a framework that cannot be gamed by hindsight. The core idea is simple. Define what normal looks like. Define what a storm looks like. Decide in advance how to line them up. Decide what would count as evidence and what would not. Then let nature run and score the result without moving the goalposts. Normal for earthquakes is not silence. Normal is a living baseline that varies by region and time since the last large rupture. A subduction margin that just produced a great event will host a long tail of aftershocks that decline in a predictable way. A strike-slip fault with no recent major rupture may tick along with small events that reflect steady loading. The first step is to model these expectations using public catalogues. For each region of interest, fit an aftershock decay curve if there has been a recent main shock, and estimate a background rate if there has not. Include uncertainty bands so that a modest rise or fall does not get mistaken for a signal. This creates a forecast of earthquake counts and sizes that does not know or care about what the sun is doing. Normal for space weather is not quiet either. The solar wind breathes, indices wander, storms come in families. We need to turn this unruly behavior into clean segments that can be compared. Choose a threshold for a storm based on upstream measurements and ground indices. For example, a period when the upstream magnetic field points strongly south for many hours, or when a global disturbance index exceeds a chosen level for a chosen duration. Select these thresholds before looking at any seismic data so the definition does not drift toward a desired outcome. Build a list of storm windows that meet the same standard. Build a list of quiet windows that match each storm in length and season, but lack the driving conditions. The timeline now has two aligned tapes. One tape lists storm windows and quiet windows. The other tape lists earthquake activity in the regions we care about. The question is not whether quakes happen near storms. That will always be true somewhere because the planet is busy. The question is whether the rate departs from the baseline more often during storm windows than during matched quiet windows, and whether any departure persists after we control for aftershock behavior and for regional differences in geology. Controls matter because both tapes are complex. Aftershocks cluster by design. If a storm happens to fall inside a rich aftershock period, the counts will look high even if the storm is irrelevant. The way to protect against this is to apply the same aftershock model to both storm windows and quiet windows. Remove expected aftershocks by modeling, or keep them in but compare like with like by matching on time since the main shock. Repeat the analysis with both choices to see if conclusions depend on the method. If they do, the effect is fragile. Geology matters because induced fields travel through conductors. A coastal basin filled with brines is not the same as a block of dry crystalline rock. If a pathway exists, it should be strongest, where the ground provides an easier route for electricity. That prediction lets us carve the map in advance. Use conductivity models, or if those are unavailable, use proxy layers like sediment thickness and known mineral belts. Tag each region as more likely or less likely to host induced currents. A real effect should show a geographic fingerprint that lines up with these tags. A random coincidence should not. A fair test also needs a clock. Triggers, if they exist, should operate within a reasonable time window after the onset of the driving conditions. Choose windows that reflect known coupling times in the geospace system. Minutes for initial field swings are too short for crustal effects. Many days are probably too long to tie to a single storm. Hours to a few days is a plausible compromise. Write the window before you look. Then for each storm, compute whether earthquake rates in that window rise above the baseline by more than the uncertainty bands allow. Do the same for the matched quiet windows. The comparison must be symmetric. It is easy to cherry-pick a single eye-catching example. It is harder to pass a population test. The goal is to ask whether the collection of storm windows shows a small but consistent tilt in the same direction. Choose a statistic that cannot be excited by a few dramatic points. For example, count how often a region shows any positive deviation during storms compared with quiet periods, or compute the median change rather than the mean. Then repeat across regions and across years. If the result survives these rotations and does not vanish when a single storm or a single cluster is removed, then we can begin to talk about a pattern. If it fades under modest changes, then we have learned that the pattern was an artifact. Pre-registration is the strongest promise we can make to ourselves. It means we publish the plan before the next storm arrives. We list the thresholds, the windows, the regions, and the statistics. We invite others to use the same script on independent data. We accept in advance that a null result is valuable. This practice, common in other fields, is rare in stormquake conversations. Adopting it would raise the quality of every claim overnight. Transparency also requires clean reporting. If one region shows a positive hint and another shows nothing, say so. If a method produces a signal only when a specific catalog is used, say so. If results depend on a narrow choice of thresholds, say so. The point is not to win a debate. The point is to learn whether nature is whispering in a way we can hear above the noise. There is a human reason to care about this rigor. Overstating links between the sky and the ground can cause unnecessary fear and distraction during real emergencies. Understating them, if a subtle link exists, can blind us to a piece of physics that belongs in the broader story of coupled systems. A fair test recognizes both risks. It chooses patience over drama and design over anecdotes. Our through line holds steady. We now have a plan for baselines and controls. We have a way to compare storms with seismic activity that resists hindsight. Next, we step back into the sky to meet the interstellar visitor and to see why comets are not just pretty, they are instruments that space built for us. Every so often, the solar system receives a guest that did not grow up here. We have proof that such visitors exist. The first confirmed one saw the light of our telescopes late in the last decade, and it carried a name that means scout. The second was unmistakably comet-like and left a long veil behind it as it passed the Sunday. Together they told us that space between stars is not empty of small bodies. It is seeded with fragments that wander for ages until gravity lends them a path through someone else's front yard. Our current story features another such traveller. It behaves like a comet, and it is moving on a path that will carry it past the sun and away again. What matters for us is not a countdown or a thrill. What matters is what an interstellar comet lets us measure about plasmas, about chemistry, and about the way sunlight turns ice into a living atmosphere. A comet is a nucleus, usually a few kilometers across, made of ices mixed with dust and more complex materials. Far from the sun, the nucleus is quiet. Closer in, sunlight warms the surface, and frozen molecules escape directly into gas. That gas drags dust into space. The result is a coma, a cloud around the nucleus that can grow to astonishing size while remaining extremely thin by any everyday standard. Within that cloud, sunlight and the solar wind set off a cascade of reactions. Photons knock electrons off neutral gas. Charged particles from the sun sweep some of the newborn ions into a long tail that points away from the sunday. Radiation pressure pushes dust more gently, which makes a second tail that can bend along the comet's path. When we look at those tails, we are looking at an equation written in light. The shape records the balance of forces in a running dialogue with the solar wind. An interstellar comet raises the stakes because its interior likely preserves a recipe from a different stellar nursery. A competing view suggests that processing in interstellar space may erase some of those fingerprints. Either way, spectra of the coma, which means the colors of light, specific molecules emit or absorb. Let researchers compare what boils out of this nucleus with what we have seen from comets that formed with the planets. Similarities would argue for common chemistry across the galaxy. Differences would hint at regional accents in the way planetary systems assemble. Both outcomes teach us something real. There is also a physics prize. A large coma is a natural plasma chamber. It builds itself, it maintains itself, and it responds to the solar wind in slow motion compared with laboratory experiments. Instruments on Earth can watch as upstream conditions change, and then watch how the coma reacts minutes to hours later. Does the ion tail kink when the interplanetary magnetic field turns? Does a change in solar wind speed produce a measurable shift in the boundary, where ions and neutrals trade energy? Repeated observations across many comets in different orbits turn these questions into a comparative science. An interstellar visitor adds a new corner case to the set. One possibility is that interstellar comets turn on earlier, at larger distances from the Sun, if their ices contain a higher fraction of species that vaporize at lower temperatures. Another is that their activity is patchy, because surface layers are more varied. It remains uncertain whether these patterns hold in a general sense, because the sample is small, and each object brings its own spin rate, size, and surface texture. What is not uncertain is that measuring the coma while the Sun is active gives us a chance to watch plasma processes across a range of space weather conditions. Stronger wind, quieter wind, rotating fields, steady fields, all of these appear in a single apparition, and the comet responds without any need for a switch we control. There is a practical payoff for heliophysics in this. Think of a comet as a buoy lost at sea that happens to drift through a storm. The buoy is passive, yet its motion allows you to infer the waves and currents around it. A coma is that buoy, but in a charged ocean. By mapping changes in brightness and structure, and by taking spectra across different regions of the cloud, scientists can back out the density and field conditions that would create such shapes. This is not a perfect inversion. It relies on models. It gives constraints rather than exact numbers. Still, those constraints help test ideas about how the solar wind couples to anything that conducts. Planets and moons do that coupling too, so each comet pass helps with that bigger map. Narratively, it matters that the visitor is not a threat. Close approaches in popular imagination are often framed as danger. Here, the geometry keeps distances large in human terms. The interesting interactions happen because plasma reaches across volumes, not because rocks fly close to cities. That difference lets us keep the mood that fits our theme. Curiosity, not alarm. Measurement, not countdown. There will be speculation around any object that glows strangely or that behaves in a way we did not expect. We mark that boundary openly. Evidence is limited, but one inference is that some features that seem exotic at first glance can be traced to the way sunlight hits a rotating, irregular surface. A minority view holds that some oddities could signal unusual structure or chemistry. Time and data decide between these views. Our job in the meantime is to keep the language honest while keeping the camera close. Show the coma, show the tail, show how both change with the wind. Then return to the timeline of storms and quakes and ask whether the presence of a giant plasma cloud in the inner system changes any of our earlier expectations. This is the connective tissue to the rest of the film. Interstellar comets are not only postcards from elsewhere. They are also working laboratories. They let us watch the solar wind at play. They give us a safe way to see how electromagnetic systems scale from laboratory size to planetary size. When the sun grows more active, the laboratory is busier. That is why this visitor arrives at such an interesting moment. Not because it causes our weather or our quakes, but because it lets us test how energy moves through the space we all share. Our through-line returns: keep the facts, label the unknowns, and let wonder do its work without leaving the ground truth. Next, we will look closely at the coma itself, how it becomes so large, and why scale matters when you try to guess whether a change in space can ever touch stone far below your feet. Picture a mountain-sized core of ice and rock drifting inward through sunlight. By itself, it is dark and modest in scale. Then the surface warms and molecules begin to lift away. Dust grains loosen and follow. What was once a bare nucleus now sits inside a fragile atmosphere that swells outward in all directions. This is the coma. It is not a solid shell. It is a vast cloud so thin that a swimmer would not notice its drag if it could be bottled on Earth. Yet in space, the coma becomes the dominant presence. It can grow far larger than any planet. It can be measured in hundreds of thousands of kilometers. That contrast between a small engine and a huge envelope is the first lesson. Small bodies can cast large electromagnetic shadows when sunlight turns them into sources of gas and plasma. The recipe is simple in principle and complex in practice. Sunlight reaches the surface. Volatile ices near that surface absorb energy. Instead of melting into liquid, many of these ices jump directly from solid to gas. This process is called sublimation. Vapor leaves through vents or porous layers and streams away. Dust rides the flow. The expanding gas cools as it moves, which encourages a balance between production and escape that sets the coma size. If production increases as the object nears the sun, the coma expands. If production drops or the wind strips material more aggressively, the coma can shrink or change shape. Rotation matters because it presents different terrains to the Sunday. Irregular shapes matter because ridges and pits create microclimates. The coma is therefore a living map of the nucleus and its day-night rhythm. Scale matters because forces act differently across its volume. Near the nucleus, collisions between molecules are more common. Farther out, the cloud becomes so thin that collisions are rare. In the inner region, gas dynamics behave a bit like a slow exhale. In the outer region, radiation and charged particles dominate. There, the solar wind and solar photons knock electrons off molecules. Newly born ions feel electromagnetic forces and rush into the wind. That is the origin of the straight ion tail that points away from the Sunday dust. Grains are much heavier and respond to light pressure and gravity instead. That is the origin of the curving dust tail that often bends along the orbit. The coma feeds both tails. It is the kitchen where the ingredients are prepared before the wind takes them away. When scientists describe coma size using giant numbers, they are not claiming a solid object. They are integrating a faint glow across a threshold of detectability. Different telescopes and wavelengths will report slightly different sizes because each is sensitive to a different species and to a different brightness level. Infrared views may emphasize warm dust. Ultraviolet views may emphasize certain ions. Visible light images show dust scattering sunlight. Radio observations can pick out specific molecules. Put together, these views outline a sphere that is real as a physical region where comet-borne material dominates the local environment, even if a spacecraft flying through would encounter only a whisper of matter. Now, to what scale does and does not imply? A very large coma can interact with the solar wind over a huge cross-section. That makes the comet a noticeable obstacle in the flow. A bow shock can form upstream. Field lines can be draped around the cloud. These effects are visible in images as kinks and boundaries. When the sun is active, those boundaries move. This is why comets serve as natural plasma probes. A large coma does not mean the nucleus threatens nearby worlds. The density of the cloud falls quickly, with distance from the source. By the time you are a few comet radii away in a human sense, the cloud is so thin that even a spacecraft can cross without damage if its path avoids the densest jets. Scale also frames the conversation about whether remote electromagnetic activity could influence anything on Earth. A coma that spans hundreds of thousands of kilometers is impressive inside the solar wind. It can seed a large region with ions. It can host currents that close through its own plasma. The question that concerns us is whether such a structure can change conditions at our planet beyond what solar variability already does. For most geometries, the answer is likely no. The energy the sun delivers to the near-Earth environment dwarfs any single comet contribution when measured at Earth's orbit. The dominant term in our electrical weather remains the orientation and speed of the wind and the structure of the interplanetary field. A comet adds a local interaction region that teaches us physics. It does not rewrite the main script for global coupling. There are narrow cases that experts still watch with curiosity. If a very large coma finds itself in a stream of fast wind that is already aimed near Earth, then the combined structure can launch waves and irregularities that travel downwind. Evidence is limited, but one inference is that such disturbances could slightly modulate the timing or shape of an arriving storm. This is a second-order effect layered on top of the first-order driver from the Sunday. It is interesting for models and for basic science, not a reason for alarm. The same logic applies if dust from the coma later crosses Earth's orbit. That can make a meteor shower months later. It does not feed energy back into the crust. Coma physics also holds a mirror to our earlier question about tiny triggers. Inside the cloud, electric fields guide ions along field lines. Collisions with neutrals exchange momentum. Small fields can redirect large volumes of charge because the density is so low. In rock, the opposite is true. Densities are high, crystal lattices lock atoms in place, and charge transport is constrained by grain boundaries and fluids in pores. This contrast explains why an electric push that matters in a cometary coma tells us little about direct leverage on deep faults. It also explains why the most realistic pathways for any space weather effect on seismic timing would involve shallow processes or engineered conductors, not a large comet far away. The visual impact of a giant coma remains powerful. It is a lantern hung in the solar wind that lets us watch invisible forces draw patterns in light. For storytellers, the image offers scale and wonder without resorting to threat. For analysts, the image offers boundary conditions. It sets the limits of what a comet can and cannot do. Both roles support the central theme of this documentary. Hold on to awe, hold on to evidence. Let scale be your compass when claims grow loud. Our through line continues. We have learned why a comet can look as big as a planetary disk while remaining gentle, and why that scale speaks more to measurement than to menace. Next, we will use that bubble as a laboratory. We will watch how comets become instruments that sketch the wind, and how those sketches help us read the larger storm that sometimes coincides with noisy days on Earth. A comet is not just an object. It is an instrument that space builds for us and then sets loose in the wind. When gas escapes from the nucleus and forms a coma, and when that gas becomes partly ionized by sunlight, the cloud turns into a responsive sensor. It drifts, it brightens, it bends, and each change records the state of the invisible medium around it. Scientists have. I learned to read these changes the way sailors read waves. A kink in the ion tail marks a sudden turn in the interplanetary magnetic field. A step in brightness maps a density jump in the flow. A moving boundary around the head of the comet traces the balance between pressure from the solar wind and pressure from the outflowing gas. Nothing here is metaphor. It is a signal written in light. The most famous signal is the tail disconnection event. From time to time, the ion tail appears to snap and drift away, only to regrow soon after. This dramatic behavior occurs when a magnetic field reversal or a shock in the solar wind passes the comet. The ions in the tail are tied to field lines that thread through the wind. When the field direction changes quickly, the lines can reconnect and leave the previous tail stranded. The new field lines carry fresh ions into a new tail that points along the updated direction. In a single frame, the comet writes down the moment the field flipped. A spacecraft sees a number on a plot. A telescope sees a blue ribbon break. Both record the same physics from different vantage points. Closer to the nucleus, the coma carries information about pressure and chemistry. The boundary where comet gas meets the oncoming wind is not sharp. It is a transition that shifts with the flow. If the wind speed increases, or its magnetic field strengthens, the boundary presses inward. If the outgassing rate grows as the comet warms, the boundary swells outward. By monitoring the size and shape of this region over days, observers can infer whether changes are driven by the sun or by the nucleus. Spectra add a second layer. Specific bands of light trace specific molecules. If a surge in one molecule appears without a matching change in the wind, the cause is internal. If all bands brighten together while the tail kinks, the cause is likely external. Reading these clues takes models and care, yet the method is robust because the comet cannot decide to lie. It simply responds to forces. Comets also reveal the texture of the wind. The solar wind is not smooth. It carries turbulence over a wide range of scales. In the ion tail, this turbulence shows up as striations and waves. The spacing of these structures and the speed with which they move downstream reflect the spectrum of fluctuations in the flow. Multiple comets in different parts of the inner system allow a kind of multi-point sampling that would be too expensive to build with spacecraft. When an active sun fills the heliosphere with varied conditions, some comets probe fast streams, while others sit in slower regions. Comparing their tails during the same week becomes a story about space weather as much as about comets themselves. The laboratory grows richer when ground-based telescopes and space missions work together. Upstream monitoring gives the input. Telescopes provide the response. The link between them is time of flight. A change in the wind measured near Earth will reach a comet farther sunward or farther outward after a predictable delay based on the geometry and the wind speed. By aligning these clocks, researchers can test whether a feature in the coma or tail corresponds to a specific structure in the wind. Successive apparitions add yet more context. The same comet, at a different distance from the Sun, will outgas at a different rate, which changes the stiffness of the interaction region. It is like testing the same instrument at different gain settings to see whether the recorded song still matches the orchestra. There is a practical benefit that goes beyond academic curiosity. Space weather forecasts rely on models that predict how energy couples from the solar wind into planetary environments. Those models need validation. Comets offer independent checks on magnetic reconnection rates, on shock strengths, and on how quickly ionization fronts move through tenuous gases. For example, if a model predicts a strong compression region, followed by the southward field, a comet downwind should show a boundary squeeze followed by a tail disconnection. If it does not, the model is missing something. If it does, confidence grows that the same physics is being captured for planets and for power grids that rely on accurate warnings. One possibility is that an unusually large coma can amplify certain signatures and make marginal solar wind features easier to detect. A competing view suggests that size is less important than the contrast between outflow and wind pressure. It remains uncertain whether a simple size metric predicts sensitivity. What is clear is that the diversity of comet activity levels gives us a range of instruments for free. Some are hot and loud, some are quiet and steady. Together, they sample different corners of the phase space that sets the rules for plasma interaction. Reading comets as instruments also disciplines our conversation about danger. The same images that fuel dramatic headlines can be used to reduce anxiety. Show the tail break, then explain it as field geometry. Show the swelling coma, then attribute it to a change in outgassing rather than a change in orbit. Show the glowing bow region, then connect it to pressure balance in a gas so thin that a vacuum pump on Earth would be jealous. Wonder does not require panic. In fact, wonder grows when viewers understand what they are seeing well enough to predict the next frame. All of this loops back to our earthquake question in an indirect but valuable way. The Comet Laboratory helps us separate large-scale electromagnetic phenomena that are well understood from the small-scale whispers that remain hypothetical. If a storm strong enough to snap a tail does not map onto a clear seismic effect, that absence becomes evidence against simple causal narratives. If a sequence of storms during a busy month shows no consistent tilt in earthquake timing after we control for aftershocks, then we have learned that the loudest signatures in space do not necessarily reach the ground in ways that matter for faults. That is not a disappointment. It is a boundary drawn with real instruments. Our through line holds. Use the comet to see the wind. Use the wind to check our models. Use both to keep the story anchored when coincidence tempts us to draw lines that nature does not draw. Next, we follow the energy downstream from the ionosphere into the systems people actually rely on every day. Power grids and pipelines do not care about poetry. They care about currents. Understanding how those currents flow will sharpen our sense of what space weather truly changes on the ground and what it leaves untouched. Begin at the top of the atmosphere, where charged particles and electric fields are at home. During a storm, the auroral zones glow because currents are flowing through the ionosphere. Those currents are driven by electric fields set up when the solar wind couples to Earth's magnetic shield. Imagine a giant circuit. The generator is far upstream in the solar wind. The transmission lines are magnetic field lines that guide energy toward the poles. The load is a sheet of current spread across the ionosphere. As those currents rise and fall, the magnetic field at the surface changes. According to Faraday's law, a changing magnetic field induces an electric field in the ground. That is the first step in the path from space to soil. The induced field at the surface is not uniform. It depends on how quickly the magnetic field varies in time and on the electrical properties of the ground. Think of the ground as a layered conductor made of rocks, sediments, brines, and crystalline blocks. Some layers carry current well, others behave like insulators. When the magnetic field above us swings, the geoelectric field that appears is shaped by this underground architecture. The same storm can produce modest fields in one region and stronger fields a few hundred kilometers away, simply because the geology is different. Long, man-made conductors are excellent receivers for these slow electric fields. Power transmission lines stretch across landscapes and return to ground through transformer stations. Pipelines follow valleys and coastlines for thousands of kilometers. Fiber optic cables often include metallic sheaths and repeaters that tie into power systems. Rail networks provide continuous steel paths that are electrically connected at regular intervals. During a storm, induced electric fields push currents into these systems. The currents are quasi-direct in character. They drift slowly, and in the case of power grids, they ride on top of the normal alternating flow. Engineers call them geomagnetically induced currents. Transformers are sensitive because they are designed for alternating currents that swing evenly around zero. A slow, direct component biases the magnetic core. That bias can drive parts of the core into saturation for part of each cycle. Saturation wastes energy as heat and produces harmonics that confuse protection equipment. Left unchecked during a strong storm, the added heat can shorten a transformer's life, or in rare cases, drive protective trips that require operators to shed load. Utilities mitigate this with procedures and with hardware. They monitor the direction and size of currents entering substations. They change operating points to add margin. In some places, they install series capacitors that block the slow component while passing the alternating component. Pipelines feel the storm as changes in their natural corrosion environment. Currents entering and leaving the pipe alter local electrochemical conditions. Pipeline operators apply cathodic protection to fight corrosion by driving a controlled current. A geomagnetic disturbance changes the background that system rides on. If the change is large and prolonged, coating defects can experience enhanced corrosion. Operators monitor potentials along the line and can adjust protection systems or temporarily isolate segments to reduce unwanted current loops. Submarine cables and coastal grids experience a special effect called the coast effect. Salt water is a much better conductor than most rocks. Where a coastline places seawater next to resistive land, the contrast enhances geoelectric fields during storms. That means coastal substations, landfalls for undersea cables, and pipelines that cross shorelines may see larger induced voltages than inland stations during the same event. Engineers include this geography in their hazard planning because the map matters as much as the magnitude of the storm. Scientists measure and model these pathways with a method called Magnetotellurics. Ground stations record magnetic and electric fields while storms sweep past. From the paired signals, they infer transfer functions that connect the changing magnetic field to the induced electric field at each site. Those functions reflect the local underground conductivity structure. When combined into regional maps, they allow forecasters to convert a predicted magnetic disturbance into a map of likely electric fields on the ground. That map is the missing link between a satellite warning and a decision in a control room. Timescale is another key. The ionosphere responds within minutes to changes in the solar wind, and the magnetic field at the surface follows soon after. The geoelectric field in the ground follows as well, but the magnitude depends on how fast the magnetic field is changing. Short, sharp swings produce larger induced fields than slow, gentle trends. This is why a modest storm with rapid fluctuations can be more troublesome for grids than a long, steady one. Rate of change sets the amplitude of the induced fields that push on long wires. Now place faults into this picture. Fault zones often lie deeper than the layers that conduct well. Some carry fluids in fractures. Some are dry and resistive. The induced fields that matter for power systems typically penetrate only the shallow crust. The deeper the target, the more the signal decays. That is the physics behind the mainstream view that storms threaten technology long before they approach the stresses that govern fault failure. There are exceptions in certain provinces where conductive belts extend deeper because of ancient tectonics or present-day brines. Even there, the power available per unit volume in the deep crust is small compared with the mechanical energy of tectonic loading. This does not slam the door on every subtle pathway. It does set a high bar for claims that invoke deep effects. The language of circuits helps prevent confusion. The magnetosphere and ionosphere form a dynamic current system that we can measure. The ground responds through induction in proportion to the pace of magnetic change and through the filter set by geology. Long conductors tie remote points together and concentrate the effect. Transformers and pipelines are therefore the front line. Bedrock is a reluctant participant. If any influence on earthquakes existed, it would likely be indirect and shallow, perhaps through changes in pore pressures near the surface or through currents that find uncommon deep paths. That is a research question, not a result we can claim. For daily life, the important part is practical. Forecasts of geomagnetic activity lead to watch states for grid operators. They adjust flows, hold spinning reserve, and reconsider planned maintenance. Pipeline companies review potentials and station data. Satellite operators change modes to reduce risk. Aviation alters routes near the poles if radio blackouts are likely. These actions convert a storm into an inconvenience rather than a crisis. The same discipline is how we should treat the earthquake question. Plan, measure, compare to baselines, and keep conclusions tethered to what the fields and the rocks actually do. Our through line remains clear. Energy from the sun flows first into the magnetosphere, then into the ionosphere, then into long conductors and shallow ground. By the time it reaches bedrock, little is left to work with. That ladder of coupling guides both engineering practice and scientific humility. Next, we examine the catalogue of small triggers that are accepted, and we ask how a space weather nudge would need to look in order to earn a place beside tides and fluids. The idea of a small push is easier to accept once you review the triggers that seismologists already allow into the conversation. None of them creates tectonic stress. None of them rewrites plate motions. They act on timing, and only when the system is perched near its limit. The classic example is the tide. The moon and the sun raise tiny bulges in the oceans and in the solid earth. The resulting stress changes are measured in small fractions of what a locked fault endures over years. Yet in some volcanic fields and along some faults that are already sensitive, the daily cycle of loading and unloading leaves a fingerprint in micro-earthquake rates. Not every region shows this modulation, which is the first lesson. The small push is selective. It appears when fault geometry, fluid content, and stress state line up in a way that lets tiny changes matter. Seasonal weather provides a second example. Heavy snow and rain add weight to the crust. Melt seasons remove it. Water seeps into pores, travels along fractures, and changes pressure in rock. These processes are slow and local. They do not flip large regions from safe to unsafe. They can change the timing of small events, and sometimes they can influence the rate of moderate events in specific settings. After exceptional rainy seasons, some areas show upticks in shallow seismicity as pore pressures relax. In mountain belts, snow load can suppress small earthquakes during winter and release them during spring as weight is reduced. The pattern depends on local geology and on depth. What matters for our story is that the trigger is not magic. It is a pressure change with a path through real rock. Human activity provides a third category. When fluids are injected into deep formations at high rates, pore pressure around pre-existing faults can rise. Effective friction drops, and a fault that was nearly ready can slip. The term used is induced seismicity. This effect has been documented in several regions where industry changed subsurface pressures quickly. The lesson is not that people cause earthquakes out of nothing. The lesson is that fluids are powerful when they find a pathway to weaknesses that already exist. Depth, pressure, and fault state decide whether a change is recorded by a seismometer or not. Reservoirs and groundwater extraction offer mirror images of the same physics. Filling a large reservoir loads the crust and can increase pore pressure beneath the dam. Some sites have shown increased seismicity after impoundment. Pumping groundwater can lower pore pressure and change stresses, which in some basins appears to modulate small events. Again, geography matters. Complex geology sets the terms. Most activities leave no seismic mark at all because the required alignment of conditions is rare. These examples illustrate three pillars in the small push debate. First, the push must have a clear mechanism. Second, the push must operate in a time window that fits the way the crust responds. Third, the push must be measured against baselines that already explain the majority of the pattern, especially aftershock decay following large ruptures. If any of these pillars is missing, the case erodes quickly. If all are in place, a modest effect can earn a cautious place in the model for a specific region. Scale and selectivity guard the gate. Tidal stresses are small, yet their timing is precise, and their pattern repeats every day, which makes statistical tests strong. Seasonal hydrology is messy, yet its signals persist for months, which allows careful separation from the background. Fluid injections are localized, yet the pressure change can be measured or modeled, which ties cause to effect in space and time. Each example has a control. Each example respects the fact that most faults will ignore most small pushes most of the time. This is the standard that any claim about space weather must meet. A storm is energetic in the ionosphere and in long wires on the surface, yet the deep crust is stubborn and often resistive. For a space weather nudge to make the list of accepted triggers, it needs a route that moves from a measured change in magnetic field to a plausible change in pore pressure or friction on a fault that is already near failure. It needs a clock that matches the hours to days that characterize coupling through the atmosphere and the shallow ground. It needs geography that predicts where the effect should appear based on conductivity structure, not where the last headline came from. It needs to survive comparison with quiet periods that are matched in every way except the state of the sky. There is a balancing act at work. Dismissing all small pushes because they are small would be unscientific. Embracing every correlation because timing feels spooky would also be unscientific. The middle path is to keep asking for mechanism, magnitude, and a design that can fail. When the push is real, it will show up in specific places and times. When it is not, the pattern will fade under the weight of properly matched controls. The debate also benefits from humility about prediction. Short-term earthquake prediction remains out of reach. Triggers do not change that. They can tilt probabilities over a window, or they can explain why a cluster appears during a particular season in a particular basin. They cannot tell a city that a fault will fail tomorrow at noon. That is why public agencies emphasize preparedness and hazard maps over announcements about days. It is why this film will not claim that a storm has scheduled an earthquake. The honest version of the question is narrower and more interesting. Can electromagnetic weather nudge faults that are already near failure in places where the ground provides an electrical pathway? If so, by how much, and how would we know? Reorientation helps keep us honest. Our through line is known versus unknown. Known, tectonic loading sets the stage, and aftershock laws describe the decline that follows a great event. Known, small changes in stress or pressure can modulate timing in specific contexts. unknown whether space weather contributes a nudge of that kind outside technology systems. The only way forward is to treat the sky as one more candidate trigger and to test it with the same discipline that tides and fluids survived. Next, we will frame the most common speculative pathway that connects storms to the ground, the idea that low-density solar wind streams create a kind of vacuum that changes how the magnetosphere and ionosphere couple to Earth. Then we will mark what the physics allows and what it likely does not, so that the test we built earlier has a target to shoot at. One possibility is this. When a high-speed solar wind stream arrives with unusually low particle density, the magnetosphere expands, and the way energy couples into the upper atmosphere changes. Advocates call this a vacuum-like state, not because space becomes empty in the literal sense, but because the solar wind that usually presses on the dayside boundary becomes thinner, even as its speed remains high. Pressure is the product of density and velocity squared. Lower density with sustained speed can reduce the ram pressure that sets the size of the magnetosphere. In response, the boundary can move outward. Field lines stretch farther, and the geometry of currents that connect to the ionosphere can rearrange. The claim is that during these episodes, the electrical environment of the polar regions and mid-latitudes shifts into a configuration that favors long-lived currents and unusual distributions of electric fields at the surface. Proponents then follow the chain one more link. If the ionospheric pattern changes, the geoelectric fields induced in the ground can change as well. In regions where geology provides conductive pathways, these fields might be stronger for a given rate of magnetic change, or they might persist longer than usual. Evidence is limited, but one inference is that such conditions could nudge crustal systems that are already primed by tectonic loading. The suggested pathways include electrokinetic effects in shallow porous rocks, small changes in pore pressure along fractures that communicate with deeper structures, or mild changes in frictional properties where clays and fluids control how a fault patch slides. The proposed effect is not to start an earthquake from rest. The proposal is to move the clock forward slightly on one that was already close. The physics that carries this idea begins upstream. Coronal holes on the Sun open magnetic field lines into space. Plasma escapes more freely along these lanes and can reach Earth at speeds well above the slower ambient flow. Sometimes those flows are accompanied by low density. At the bow of the magnetosphere, pressure balance determines how far the boundary stands off. Lower pressure outside allows the boundary to relax outward. That relaxation can alter where reconnection occurs on the day side and how energy is stored in the magnetotail. It can also change the voltage that maps along field lines into the ionosphere. Measurements during such intervals often show clear signatures in ground magnetometers and in auroral cameras. The sky is telling us that the circuit has changed its operating point. What remains uncertain is how often these upstream conditions align with the ground effects that matter for the small push problem. The induced electric field at the surface depends strongly on the rate of magnetic change, not only on the absolute configuration. Low-density streams can be quiet in that sense because they sometimes produce smooth drifts rather than sharp swings. If so, the induced fields are modest. On the other hand, interfaces between fast and slow wind can carry sharp structures and embedded waves. When those pass over a region with favorable geology, the ground response can be larger for a short time. A competing view suggests that the dominant factor remains the orientation of the interplanetary magnetic field and the presence of sudden impulses, which occur during compressions rather than during relaxed pressure states. In that view, the vacuum idea is secondary, because the strongest coupling events arrive with higher density or with shocks that drive rapid field changes. A careful framing helps. The vacuum hypothesis is not a single claim. It is a family of related conditions that includes low density, high speed, and long duration driving from open solar field regions. The combined effect can create sustained convection in the magnetosphere with a lower overall pressure at the boundary. That can change how currents flow in the ionosphere and where electric fields appear at the surface. If any influence on faults exists, the best chance to see it would be during hours when three filters line up. First, the solar wind must be in one of these low-density states with coherent driving. Second, the ground beneath the region of interest must contain conductive structures that help induced fields reach depth along natural channels. Third, the seismic system must already be near failure, which is most likely during the early decay of an aftershock sequence following a great event. Without all three, the path is probably too weak. How would we test this without fooling ourselves? We would pre-select storm windows by upstream density and speed, rather than by ground magnetometer drama alone. We would rank windows by how low the density falls and how long it stays there. We would then mask the map by geology to mark where induction should be strongest. Finally, we would compare earthquake rates in those windows with matched quiet windows and with windows of different storm types, for example fast dense streams or mass ejection passages. If a pattern appears only during the low density class and only in regions where induction is favored, and only during periods when seismicity is already elevated for local reasons, then the idea has survived several gates. If the pattern appears equally during unrelated storm types or in resistive provinces or during quiet seismic months, then the idea has failed. Scale remains the guard. Laboratory studies show that electric fields can influence friction in wet clays and that currents can alter electrochemical conditions in rock. These effects are small and depend on direct exposure to fields much stronger than the fair weather field near the surface. To map such results onto natural faults, the fields would need local amplification through conductive channels, and the target would need to be shallow. Deep locked segments inside dry crystalline rock are unlikely to notice. Shallow fault zones laced with fluids might respond weakly. This selectivity turns a sweeping claim into a narrow and testable one. That is progress, even if the final answer is negative. There is one more practical constraint. Energy from the sun does not arrive with intent. It arrives with structure set by the solar surface and by the path through the heliosphere. If a clock shift exists, it should not pick favorites among coastlines or countries. It should respect the map of conductors and the map of active fault systems. A minority view holds that planetary alignments can modulate these conditions independent of wind properties. The mainstream view gives the wind and the magnetic field primacy. Our test should reflect that primacy. Choose windows by measured density and field direction. Let the geometry of the wind decide when to look. That keeps the hypothesis inside physics and outside. Numerology. Our through line remains. Take a speculative path, write it in the language of mechanism and scale, and then tie it to a plan that can fail. Next, we turn to the alignment argument itself, because it often rises whenever timing coincidences gather. We will listen to the claim that planetary geometry matters, and we will mark why most heliophysicists consider that geometry a weak lever compared with the wind and its magnetic field. When strange timing puts space and ground events near each other, a familiar idea re-enters the room. Perhaps the planets lined up and tuned the solar system like strings on a harp. The image is elegant. The physics is less generous. A competing view, which is the mainstream in heliophysics, holds that planetary geometry has little to no direct leverage over the processes that drive geomagnetic storms or the timing of earthquakes. The reasons are simple. Forces weaken with distance. The sun cares about magnetic fields and plasma flows. Gravity from small worlds at millions of kilometers barely nudges that stage. Earth's crust cares about stress where rock meets rock. Gravity tides already exist and are accounted for, while additional pulls from planetary alignments are tiny compared with what the moon and the sun already supply. Start with the Sunday. Space weather begins when the solar magnetic field rearranges itself. That rearrangement accelerates plasma and shapes the solar wind. The important variables for Earth are the speed of the wind, its density, and the direction of the magnetic field embedded in it. These are set by the magnetic topology on the sun and by how that topology evolves over hours to days. Planets do contribute gravitationally to the overall orbital dynamics of the solar system. They do not rearrange the magnetic carpets that decorate the solar surface on human timescales. The sun is a magnetized ball of plasma with its own internal engine. It is not a pendulum that planets can push into a storm. Next, consider geometry. A conjunction is when two objects appear in the same direction from Earth. An opposition is when they sit on opposite sides of the sky. These alignments change viewing perspective. They do not bring bodies significantly closer. The gravitational effect of a planet on the sun during a conjunction is essentially the same as during any other configuration at that distance. Any small variations are lost in the massive background of solar convection and magnetic turbulence. There is no known mechanism by which a line drawn through 2 or 3 planets can flip a magnetic field line in the solar corona or launch a mass ejection toward Earth. Now consider Earth. The crust responds to tides from the Moon and the Sun. These are measurable and predictable. If planetary alignments beyond this pair mattered for crustal stress, we would expect to find a consistent modulation in seismic catalogues that follows the known periods of those alignments. We do not. Studies that assign significance to particular alignments often select short time windows or specific regions after the fact. When the windows are widened or the regions are shifted, the signal fades. This is exactly what you would expect if the result were a product of selection rather than a real force acting across the globe. There is also a scale argument that does not require advanced mathematics. The gravitational pull from a planet declines with the square of distance. The Moon is close, the Sun is massive. Both create tides that matter. A distant planet is neither close nor massive compared with the Sun. Its contribution to Earth tides is many orders of magnitude smaller than the lunar tide. If tiny tidal stresses can sometimes modulate microseismicity, that is because the lunar and solar tides are already the largest periodic players in the system. Adding the effect of a planet that is a dot in the sky does not produce a new and significant stress. It adds a ripple that is lost in the noise of local geology, atmospheric pressure changes, and hydrology. Proponents sometimes point to the heliospheric current sheet as a candidate for alignment effects. The current sheet is the vast surface in space where the polarity of the solar magnetic field changes sign. It is warped and spiraled by solar rotation. The claim is that planets crossing this structure, or lining up along it, could change electrical conditions through the inner heliosphere. The difficulty is that the current sheet is a consequence of the solar field, not an independent object. Its shape and influence are set by the Sunday planet. Positions do not control its warps. Moreover, coupling at Earth depends on the field direction that actually arrives in the wind near our orbit, which is measured by satellites. That measurement already tells us whether the latch is aligned for strong coupling. There is no need to infer anything from planetary geometry. Another recurring motif is resonance. The word has a precise meaning in physics. A system resonates when a periodic driving force matches a natural frequency of that system and energy builds up over time. The magnetic field of the Sun does have natural timescales. So does Earth's magnetosphere. The periods of planetary alignments are not matched to those timescales in any way that produces sustained energy transfer. Without a match, there is no resonance. Without resonance, there is no coherent build-up. The idea remains a metaphor rather than a mechanism. Why does this matter to our story? Because aligning coincidence with causation is the easiest mistake to make when the sky is busy. A planetary conjunction near a storm is photogenic. A planetary conjunction near an earthquake is dramatic. The mind wants a line to connect them. The science wants a path. The path is missing. What connects the Sun to our magnetosphere is magnetic reconnection and plasma pressure. What connects our magnetosphere to the ground is induction through a layered and mostly resistive crust and through the long wires we have built. Planets do not sit on these paths. The wind and the field do. A fair accommodation of the alignment idea is to use it as a reminder to be careful with timestamps. When a storm arrives, check the upstream field. When a quake occurs, check the aftershock model and the regional stress state. Then ask whether anything in the geometry of planets adds information beyond those checks. So far, the answer has been no. That no is not hostile. It is simply a recognition that physics already provides the knobs that matter. Where knobs are missing, curiosity should turn to places where the coupling is known to occur. For example, the structure of the solar wind, the conductivity of the ground, or the presence of fluids in faults. Our through line returns. Known, the wind and the field set space weather. Known, the moon and the sun set the tides. Unknown, whether specific solar wind states can nudge faults that are already close to failure in places where geology helps. Alignments make beautiful sky charts and calendars. They do not steer the engines in this story. Next, we pivot from geometry to timing windows that can be tested. If a subtle link exists, it should live in hours to days after specific solar wind signatures, not in the pose of distant planets against the backdrop of stars. Evidence is limited, yet one inference is both modest and powerful. If there is any real nudge from electromagnetic weather on faults that are already close to failure, the signature should live inside specific timing windows that begin after specific solar wind conditions arrive. That is a statement we can test. It does not require belief in hidden forces. It requires clocks, catalogues, and the discipline to compare, like with like. Start where the clocks begin. A space storm that matters for coupling to Earth begins upstream at satellites that sit sunward of our planet. They measure wind speed, density, and magnetic field direction. The journey from that point to the magnetosphere takes minutes. The magnetosphere couples energy into the ionosphere within minutes more. Ground magnetic variations rise almost immediately. Induced geoelectric fields appear with the same pace. Anything that depends on those fields reaching shallow geology would therefore begin on the scale of minutes to hours. Anything that depends on fluids moving inside rock would require additional time to propagate from shallow layers into fault zones. That shifts the expectation toward hours to a small number of days. If the proposed mechanism relies on a long-lived reconfiguration of currents in the near-Earth environment, the window could last a little longer, but it should not drift into weeks or months. If it does, it becomes impossible to separate from normal aftershock decay and from other slow processes that modulate seismicity. These physical clocks suggest a simple template for timing windows. A near window that spans the first day after the onset of strong coupling. An intermediate window that spans the next 1 to 2 days. A late window that spans days 3 to 5. The near window tests immediate induction and shallow electrokinetic effects. The intermediate window allows for fluid diffusion through connected fractures that lie close to the surface. The late window catches slower responses without inviting every coincidence into the frame. Windows defined this way can be written down ahead of time. They are not moved later to hug a curve. With windows in hand, we next define the triggers that start them. The most defensible triggers are direct measures of coupling potential, a sustained southward turn of the interplanetary magnetic field, a rapid increase in the rate of ground magnetic change, the passage of a sharp compression followed by a strong field orientation, the entry into a long, low-density, high-speed stream that reorganizes convection patterns. Each trigger can be detected by objective rules. When the rule is met, a clock starts. When multiple triggers occur close together, we can treat them as a single composite event, or we can apply a priority rule. Either choice should be written before analysis begins. Testing windows against earthquakes requires care with baselines. The correct comparison is not storm day versus any random day. The correct comparison is storm windows versus matched quiet windows that share season and time since the last large local rupture. Quiet windows are selected from periods when upstream conditions were mild and when ground magnetic activity stayed inside a low band. Each storm window receives a partner quiet window of identical length, placed as close in time as possible without overlap. This matching reduces the impact of slow, seasonal, or catalogue changes that have nothing to do with storms. There are several ways to score the outcome. One approach uses counts above a modeled expectation. For each region, we estimate the expected number of earthquakes in each window, using either background rates or aftershock laws that have been fitted without reference to space weather. We then compute the deviation from this expectation during storm windows and during matched quiet windows. If a subtle nudge exists, the distribution of deviations should tilt slightly positive in storm windows compared with quiet ones. Another approach uses a hazard model. Here, the clock starts at the trigger time, and we model the conditional probability of at least one earthquake of a given size appearing within each window. The comparison is again storm versus quiet. A third approach uses survival analysis. For aftershock sequences, we ask whether the time to the next event after a trigger is shorter during storms than during quiet periods, after controlling for the overall decay rate. Each method needs protection against multiple comparisons. We will be tempted to slice the data by magnitude, by depth, by region, and by storm class. Every slice invites a false positive if judged in isolation. The remedy is to decide on a small set of primary tests and to treat the rest as exploratory. Corrections for multiple testing keep the primary claims honest. Exploratory findings become hypotheses for the next round, not conclusions in this one. Geography should enter the test as a prior. Regions with conductive sedimentary basins or brine-rich belts are more likely to show induction at depth than dry cratons with resistive rock. That does not prove an effect, but it strengthens a detection if one appears where physics says it could. Conversely, an apparent signal that pops up in resistive terrain while conductive coasts remain flat is a red flag. Integrating conductivity maps or magnetotelluric transfer functions into the analysis is therefore not a flourish. It is a filter that separates interesting hints from catalogue noise. Timing windows must also outlive a single headline. It is easy to draw a window around one dramatic week and declare victory. A real effect should persist across years and across many storms. That is why pre-registration matters. It fixes the windows and the triggers before the next solar rotation. It forces the test to face unfavorable samples as well as favorable ones. It invites other groups to run the same script on independent catalogues and on different continents. Convergence, under those conditions, is the only path toward confidence. There is a final reason to love timing windows, even if they deliver null results. They teach us how to think cleanly about cause and effect under uncertainty. The exercise of defining clocks from first principles, matching windows properly, and scoring outcomes with restraint has value beyond the stormquake question. It keeps science honest when the world is noisy. It also keeps public communication grounded. Viewers deserve to know that when a storm and a quake appear near each other on a timeline, the relevant test is not a single overlap. It is whether similar windows, across many storms and many regions, show a small and repeatable tilt. Our through line remains known. The coupling from solar wind to ground fields operates on minutes to days. Known, aftershocks and background rates set most of the seismic timeline. Unknown, whether a slight preference hides inside these well-defined windows. The next step is to write predictions that can be wrong, and to decide in advance what would change our minds. With that in place, we can scan the sky for the next natural experiment without leaning on coincidence to write the answers for us. Predictions are the edge where a story meets the world. If a real nudge from space weather exists, it should leave footprints that are small, selective, and testable. The footprints should appear in places and times that physics already points to, not wherever headlines cluster. They should survive when the same test is run by different groups on different catalogues. They should fade when we scramble the clocks, or when we move the windows to days that only look exciting in hindsight. With that bar in mind, here is what we would expect to see if a link is real, and how we would break it if it is not. First, the time signature. After a clearly defined coupling trigger, the probability of one or more earthquakes in an affected region should rise slightly above a pre-computed baseline within hours to a few days. The rise should be measurable but modest. It should appear most clearly in the near and intermediate windows we set earlier. If the same rise appears weeks later, the claim weakens because the window has drifted into the realm where aftershock decay and normal variability dominate. If no rise appears in hours to days across many triggers, the claim fails. Second, the geography. Regions tagged in advance as electrically favorable should shoulder most of any observed effect. Coastal basins with conductive sediments, rift zones with brines, and belts where magnetotelluric surveys show strong conductors should carry the load. Stable cratons with resistive rock should be quiet. A credible pattern would show a gradient that respects these tags. A scattered pattern that lights up resistive interiors while leaving conductive coasts flat would be evidence against the link. Third, the dependency on solar wind class. If low-density, high-speed streams are the favored state for a vacuum-like configuration, then storm windows selected by those upstream conditions should outperform windows selected by unrelated geometries. Conversely, if sudden compressions with sharp magnetic changes are the true driver, then windows keyed to those impulses should carry the signal. A real effect should choose a class and stick with it. A result that jumps from class to class depending on which month we analyze is a red flag. Fourth, the magnitude range. A modest nudge should tilt the timing of small to moderate events in already active sequences. It should not conjure great earthquakes in quiet regions. We would expect the clearest statistical hints in magnitudes that occur often enough to allow clean counting, and in clusters that are already elevated after a main shock. If the only claimed signals involve large solitary events with no surrounding activity, the burden of proof becomes prohibitive. Fifth, the control tests. Null models are not an afterthought. They are the guardrails. We should scramble trigger times across the same seasons and recompute the statistics. We should swap storm windows for matched quiet windows and confirm that any tilt disappears. We should thin catalogues to simulate changes in detection thresholds and verify that the pattern does not arise from reporting artifacts. We should run the same script on regions where the geology predicts a weak response. A signal that vanishes under these controls is not a signal, it is an illusion. Sixth, the cross-method consistency. Different scoring methods should agree on the direction of any tilt. Counts above expectation, survival models for time to next event, and conditional probability models should all point the same way within uncertainty. If one method lights up while the others do not, then the effect is fragile or the method is biased. Agreement across methods does not guarantee truth, but disagreement warns us to slow down. Seventh, the repeatability across solar rotations. Many high-speed streams recur every few weeks as the sun turns. If a given stream produces a hint in one rotation, we should look for a similar hint when that stream returns, after allowing for differences in background seismicity. If the effect reappears with the stream and then fades when the stream is absent, confidence grows. If it appears once and never again despite similar conditions, skepticism wins. Now to falsification. The link fails if pre-registered windows show no tilt across a large sample. It fails if geology tags do not predict where hints appear. It fails if the same tilt is found just as often in quiet windows as in storm windows. It fails if the apparent pattern collapses when we adjust for aftershock decay, or when we remove a single headline week from the analysis. It fails if the strongest results come from regions whose catalogues changed instrumentation mid-study without correction. Most importantly, it fails gracefully. A null result is not a crisis. It is a boundary that lets us focus on what space weather surely changes, which are the technologies and the skies, not the deep stones. Predictions also help with communication in the moment. When a storm watch is issued, a responsible message would say that power grids and navigation might be affected. It would not say that earthquakes are due. If the region is in an active aftershock sequence, and if the storm fits a pre-registered class that we study, we can add that researchers are watching timing windows as a natural experiment. That is curiosity without alarm. It is science conducted in public view, with promises made ahead of time. There is one more usage for predictions in this story. They allow us to navigate wonder without getting lost. The sky will always offer coincidences. Headlines will always place images of aurora next to images of cracked highways. Our brains will always draw lines. Predictions that can be wrong give us a way to hold that instinct in check. When the windows do not show a tilt, we say so. When the tilt appears where and when physics pointed and survives controls, we say so with humility and with the caveat that small does not mean global. Our through line endures. Known, the engines of space weather and the mechanics of aftershocks. Unknown, whether a small selective nudge lives in hours to days after specific solar wind states, and only in places where conductors and fluids open shallow doors. Next, we widen the frame to the comet-rich heliosphere that shares the stage this season. Many natural probes are in play at once. Their responses offer a cross-check on the models that forecast the very storms we are studying. When more than one comet is active in the inner system at the same time, the sky becomes a gallery of living instruments. Each object outgasses at its own rate. Each spins with its own rhythm. Each moves through a slightly different corridor of the solar wind. Together, they create a natural sensor network that no agency could launch. The value of this overlap is not only beauty, it is comparison. With several comets and tails responding at once, we can separate what belongs to the wind from what belongs to the nucleus. We can test models that predict how pressure, field direction, and turbulence sculpt plasma environments. We can also check whether dramatic space weather episodes that touch many instruments leave any trace in the timelines on Earth after we control for the busy business of aftershocks. Imagine 3 comets spread across longitudes in the inner heliosphere. One rides a lane of fast wind that left an open magnetic region on the Fosco. Sunday, one crosses a slower stream full of small-scale fluctuations. One moves near the interface where fast wind overtakes slow wind and piles it into a compressed zone. A strong turn in the interplanetary magnetic field rolls through this sector over 2 days. Telescopes record tail kinks that appear first near one comet, then later near another, as the structure drifts with the wind. This is a classic time-of-flight experiment. The sequence lets us infer the size and speed of the structure that passed. It also checks how faithfully our models advect features through space. The comets become mile markers on a river that would otherwise look uniform from a single boat. Diversity in the swarm also clarifies chemistry and morphology. A quiet comet with a modest coma acts like a small microphone. It hears sharp notes and records them cleanly. A vigorous comet with a sprawling coma behaves like a large diaphragm microphone. It integrates over a wider region and responds to broad changes more than to small ripples. When both types are present, and when both show the same gross features at the correct delays, confidence grows that we are reading the wind correctly. When they differ, the difference becomes a clue about how outgassing rate and nucleus texture tune sensitivity. Overlap matters most during active solar months, when streams and shocks parade through the inner system. Even a simple map of tail angles across the swarm carries information. If every ion tail in one quadrant points at a similar slant, the field there must share a common direction. If a disconnection event cuts several tails within a day, a field reversal likely swept the region. If one comet shows a boundary squeeze without a field reversal, the pressure must have jumped. These inferences are the raw data of heliophysics. They feed back into how we forecast coupling at Earth and at other planets. The swarm has another payoff. It supplies control cases for the human tendency to link cosmic drama to ground events. When a major space storm arrives, some comets will be well placed for signatures, others will sit in quieter lanes. The presence of both lets us check whether we are overreading coincidences. If the storm coincides with a noisy week in a tectonically active region, that is a temptingly tidy story. The fair way to test the story is to ask two questions at once. Do the comets in the storm lane show the textbook responses? Do earthquake timelines in geologically favorable regions show any small and selective tilt inside the pre-registered windows? Only when both answers align with our predictions should we allow ourselves to lean forward. If the comets give a clear yes, while the earthquake windows give a calm no, that contrast is a useful conclusion by itself. It tells us that energy took the path we know and did not wander into stone. Because comets are passive, they are honest. They do not add their own power. They do not hold opinions about geometry. They do not report late because they had a busy day. They feel the field and they show it. That honesty is why a swarm is such a strong antidote to wishful thinking. The same storm that tempts us to infer a hidden crustal effect also paints a visible signature across several comae. If the signature fades when we forecast it should blaze, the models need work. If the signature blazes while the ground stays quiet within uncertainty, then the space-to-stone leap likely fails the scale test we have emphasized since the start. There is also a quiet lesson in null cases. Sometimes, a month passes with modest solar wind structure, while seismic catalogues still show clusters for reasons that belong entirely to the crust. A swarm in such a month gives us a string of flat baselines in the sky. Tails steady, boundaries steady, spectra steady. That calm becomes a background against which the next month will stand out. It also breaks the habit of attributing every uptick on Earth to the sky, because the sky is visibly uneventful and yet the ground keeps its own schedule. Overlap helps power the falsification steps we outlined earlier. If a given high-speed stream produces a consistent tail pattern across its next 2 or 3 returns, then we can pre-declare the windows for potential ground effects tied to those returns. If the windows fail across multiple returns while the comet signatures remain strong, we have a graceful way to retire the claim for that class without drama. The same logic applies if a mass ejection slices tails, but the matched windows in conductive coastal belts show no timing tilt in earthquake rates. We gain knowledge either way. We learn which storms matter to technology and to the aurora. We learn which storms pass through the crust without a trace. The human gift of this swarm is perspective. Many instruments, one wind. Many comets, one star. Many quakes, one planet. Overlay the 3 maps and you see why science craves comparisons. They keep us honest when the mind wants a single clean story. The clean story here is already beautiful enough. The sun shapes a river of charged particles. Comets drift through and reveal the river's currents. Earth sits within reach of this weather and responds strongly in the sky and in our wires. The crust mostly minds its own enormous business. If there is a nudge, it is a whisper in a few specific places and times. If there is not, then the wonder remains undiminished. Our through line holds. Use the swarm to cross-check space weather models. Use the models to set fair windows on Earth. Use both to prevent coincidence from masquerading as cause. Next, we leave the sky for a moment and look closely at the true front lines on the ground. Power grids and pipelines are where space weather always leaves a mark, and their stories help us size claims about what deeper layers can feel. The most honest way to measure what space weather can change on Earth is to watch the systems that respond every single time. Power, grids, feel it. Pipelines feel it. Satellites feel it. Aviation and navigation feel it. These sectors offer a record written in alarms, in voltages, in orbital drag, and in routes that bend around radio shadows. Their stories are not speculative. They are case studies with logs and hardware on the line. Understanding them gives us scale. It also gives us discipline when we ask what deeper layers of rock might notice. Start with the grids. A strong geomagnetic disturbance is an electrical storm for transmission networks. As currents flow through the ionosphere, the magnetic field at the surface changes. That change induces an electric field that spans wide areas. Long power lines pick it up and carry slow currents into transformers. In a modest storm, these currents are small. In a severe storm, they can bias transformer cores and drive partial saturation on each cycle of the alternating current. Operators see this as heat and as harmonics that trip alarms. The famous blackout in eastern Canada during a strong storm late in the last century is a clear example. Protective devices opened, and a large area went dark for hours. Subsequent storms during the early 2000s forced utilities to revise procedures, to add monitoring, and to develop playbooks that include increasing reactive power reserves and holding more generation on standby when watches are issued. During recent years, we have seen storms that produced vivid auroras while the lights stayed on precisely because these playbooks exist. The lesson is that space weather produces a known class of current that technology cannot ignore, and that engineering can reduce risk by treating forecasts as weather on a different spectrum. Pipelines experience the same storm as a chemistry problem. They are immersed in soil that becomes part of an electrical circuit when geoelectric fields appear. Current enters and leaves the pipe at coating defects and at bonds. The resulting shifts in potential at the pipe surface can hasten corrosion in spots that would otherwise be quiet. Operators combat this with cathodic protection systems that apply a controlled countercurrent. During storms, the background field changes, and the controlled current must be adjusted. Sensor logs from long pipelines show clear wiggles during space weather episodes. Those wiggles are not abstract. They tell crews when to tweak protection settings and when to inspect after the event. Coastal crossings are especially sensitive because seawater conducts far better than most rocks. The contrast between ocean and land enhances induced fields near shore. That is why landfalls for undersea cables and coastal substations receive extra attention in forecasts. Satellites live in the region where the storm is born. Particles accelerate, and swarms of energetic electrons can penetrate spacecraft shielding. Charging can build up on surfaces and across dielectrics. A discharge can upset electronics. Operators mitigate by changing modes, by delaying sensitive operations, and by allowing extra margin on power systems. There is also the issue of drag. During storms, the upper atmosphere heats and puffs outward. Low-orbit satellites plow through denser air and lose altitude more quickly. An event a few years ago caused a batch of newly launched small satellites to re-enter prematurely because the atmosphere swelled more than expected during a period of strong geomagnetic activity. Engineers folded that lesson into models and now watch density estimates carefully when planning low-orbit maneuvers. Aviation witnesses the storm through the sky itself. High-frequency radio relies on predictable refraction in the ionosphere. During disturbances that layer ripples and its behavior changes. Polar routes that normally use skywave communications can become unreliable. Airlines reroute across lower latitudes or lower altitudes, where different communications are available. This increases fuel burn and time but keeps safety first. The timing of these changes follows indices that track the ionosphere and auroral activity. That causal chain is well established. It runs from solar wind direction and speed to magnetospheric coupling to ionospheric currents to radio conditions. There is no need to invoke deeper effects to explain the operational choices that crews and dispatchers make. Navigation is sensitive to the same layer. Global navigation satellite systems depend on precise timing and on signal paths that travel through the ionosphere to receivers. During storms, the total electron content varies in time and space. Signals arrive with small delays that vary from place to place. Correction models handle ordinary variations. Strong storms can outpace those models temporarily. Accuracy degrades, and position solutions wobble. Survey teams and precision agriculture pause or switch to local corrections. The problem resolves as the storm relaxes. These frontline stories have two common features. They come with clocks that match the physics we have built earlier, and they come with levers that operators can pull. Warnings go out hours in advance, based on upstream measurements. Grids hold reserves, pipelines adjust protection. Satellite teams switch to safe modes. Airlines bend routes. Farmers and surveyors adjust their schedules. The presence of practical levers tells you that the coupling is strong and well understood. It is the same reason aurora tourism has schedules now. The chain from the sun to the sky over a lake is robust enough to plan around. Contrast this with claims about earthquakes. There is no lever, there is no immediate control. The geology is not a tuned instrument in our hands. If a small nudge exists, it would live within the noise floor of natural variability. That is why the path from the storm to the crust remains a research question rather than an operational platform. It is also why the technology case studies are so useful to our story. They establish the magnitude of effects we can see and manage. They keep our expectations realistic for what cannot be seen or managed in the same way. There is a final lesson in the way utilities and space operators treat forecasts. Pre-committed thresholds guide action. They decide what index values trigger a shift in procedures before the storm arrives. They write down success and failure criteria. Then they review after the event and adjust the plan. This is exactly the culture that the stormquake idea should borrow. Do not move windows after the fact. Do not cherry-pick regions. Decide in advance and let nature grade the exam. Our through line remains steady. Space weather is real, where we can measure currents and fields, and where we have built long conductors and sensitive electronics. The sky glows, the wires hum, the pipelines drift in potential, the airplanes turn. These are the signatures that anchor scale. If the crust listens at all, it listens faintly and briefly, and only in places where shallow pathways exist. Next, we return to the ground to study one region where tectonics provide a natural experiment. We will look at how a great earthquake sets the clock for aftershocks, and how any proposed external nudge would need to rise above that powerful internal rhythm to be visible. When a fault lets go in a great rupture, the planet writes a timeline for us whether we are ready to read it or not. The main shock rearranges stresses across hundreds of kilometers. The crust does not heal in silence. It answers with aftershocks that taper in time and shift in space, as locked patches adjust, and as edges of the rupture zone find new balance. This predictable decline is our metronome. Any outside nudge that hopes to be heard must rise above this rhythm without moving the goalposts after the music starts. Consider a large subduction margin where an oceanic plate dives beneath a continent. The geometry favors wide ruptures and long reach. When a great event occurs, the immediate surroundings light up with aftershocks. The rate is highest in the first hours, then falls in a way that has been measured across many sequences. The pattern is often summarized by a simple law that says the number of aftershocks per unit time declines roughly as 1 over time since the main event, plus a small constant. The exact parameters vary from place to place, yet the shape is familiar. Superimposed on that time decay is a spatial structure. Aftershocks cluster along the edges of the main rupture, along splay faults that branch upward, and within volumes where stress has increased due to the slip. Other regions near the rupture see a drop in activity. Those are the stress shadows where failure became less likely for a while. This structured decay is not an academic flourish. It is the baseline that any claimed trigger must respect. If a storm in space were to nudge the timeline, the signal would appear as a small deviation from the expected decline during a well-defined window. The deviation would be spatially selective as well, because stress changes from the main shock did not land evenly. The most likely places to see a tilt are sections that received increased stress and that host fluids or weak minerals. Conductivity maps would narrow the search further, because any geoelectric path that could carry a change from the surface into shallow crust would respect geology. Without all of these filters, a bump in counts is only a bump. The hours and days after a great rupture also contain many endogenous cues that can imitate an external push. Dynamic stress from the main shock sends waves that circle the planet and return. Slow slip on neighboring segments can begin quietly and modulate rates nearby. Delayed failure on damaged asperities inside the rupture zone can produce clusters that look like new triggers when they are simply the local system settling its accounts. Fluids that were squeezed during the main shock can migrate into fractures and change effective pressure at fault patches. All of these can produce pulses on the timeline. None requires help from above. This is why the first tool we reach for is a model fitted to the sequence itself. It captures the natural rise and fall so that residuals have a fair chance to reveal anything extra. Let us make this concrete. Suppose a great event has occurred on a subduction boundary, and we are now 1 month into the sequence. Daily counts still sit well above background, yet the decline is smooth when averaged over several days. Upstream monitors report a period of strong coupling in the magnetosphere that begins at dawn on a given day. Our pre-registered plan sets a near window of 1 day and an intermediate window of 2 days that follow. We already computed the expected counts in these windows from the sequence history. We already tagged the map with conductivity predictions and with stress change estimates from slip models. We do not move these pieces now that a storm has arrived. If a nudge exists, we would expect a small positive residual in the aftershock rate within one or both windows, focused in the sectors that both gain stress from the main shock and that sit above conductive structures. The size of the residual should be modest, because tectonic stress does the heavy lifting and because induction into rock is filtered and weak. The timing should be coherent across the windows of many storms of the same class. The pattern should not require us to re-weight the sequence or to exclude inconvenient hours. Most crucially, the same calculation performed on matched quiet windows should not produce the same residual. At the same time, we have to allow the sequence to be noisy. Aftershocks do not arrive on an even schedule. The variance is large. A day with several moderate events can tilt a weekly total, even if no trigger exists. That is why a single sequence is not enough for confidence. A robust claim would survive across several great events on different margins, across different solar wind states, and across different catalogue qualities. It would remain when we remove the most dramatic day from the analysis. It would remain when we change magnitude thresholds within reasonable bounds. It would remain when independent teams use similar plans on independent data. The advantage of treating the aftermath of a great rupture as a natural experiment is that we already know where the system is most sensitive. The stress map from the main shock points to edges and asperity zones. The slip distribution points to places where fluids may have been mobilized. The coastal geology often points to basins that can carry induced fields more readily than crystalline hills. These maps are not perfect, yet they let us write down prior expectations. A small outside push that respects these maps and appears in pre-committed windows would be notable. A bump that ignores them and arrives late is likely a passenger on the local train. There is also a public safety angle to getting this right. After a great earthquake, communities are on edge. Rumors travel quickly. If we oversell outside triggers, we risk feeding anxiety about skies and storms at a time when practical concerns deserve attention. If we undersell the complexity of aftershocks, we risk making people expect silence after a week when the physics says the tail is long. Clear communication benefits from the same discipline as analysis. Explain the expected decline. Explain stress shadows and bright spots. Explain that storms can affect power and communications, and that these services may be busier during the same week for reasons that have nothing to do with faults. Then, if we are running a study, say that we are watching specific hours with a clean plan, and that most sequences will show nothing beyond their own internal mechanics. Our throughline continues. Known, a great rupture writes a loud script that fades with time. Known, that script has features that can masquerade as triggers if we do not model them. Unknown, whether any small and selective deviation hides inside well-defined windows tied to measured space weather states. Next, we scale the idea down and look at smaller faults and intraplate regions where the background is quieter, so that a real nudge, if it exists, would have fewer natural drums to drown it out. An aftershock sea can hide a ripple. That is why it helps to look where the water is still. Intraplate regions away from plate boundaries give us that stillness. Their background seismicity is low. Their faults are shorter and often older. Their catalogues are sparse yet steady. If a small and selective nudge from space weather exists, then a quiet region offers fewer natural drums to drown it out. The cost is that events are rare. The benefit is that each one stands out clearly against a flat baseline. Designing a fair test here means trading sample size for clarity and writing rules that respect the different rhythm of these interiors. Start with the baseline again. Intraplate catalogues often resemble a Poisson process at modest magnitudes. The rate in a given province is low and roughly constant over long stretches. Local clusters do occur, usually because a small fault patch wakes up for a while. The first job is to map the background rate and its uncertainty. A moving average will do if the catalogue is long and the rate is stable. A Bayesian rate model may help if the catalogue is thin, because it allows the uncertainty to stay honest when the counts are small. Either way, the aim is a quiet expectation that does not accidentally inject structure where none exists. Next, consider geology. Quiet does not mean simple. Many intraplate settings contain sedimentary basins, salt layers, or ancient shear zones that conduct better than the crystalline bedrock around them. Magnetotelluric surveys and gravity maps can reveal these features. If a storm were to induce fields that matter at shallow depth, those structures would be the natural paths. Tag them before any analysis begins. The tags will be sparse, just as the events are sparse, yet they give the test a physical anchor. A detection that favors these tagged corridors is more credible than a detection that wanders. Triggers and windows can be lifted from earlier parts of our plan with a few changes. The clocks that govern ionospheric coupling are the same: minutes to hours for fields, hours to days if fluids are part of the path. The windows we defined earlier still make sense. What changes is the scoring. With low counts, we cannot rely on rate shifts in many small bins. We need statistics that make sense for sparse data. One approach is a conditional point process model, where the probability of at least one event in a window is the variable of interest. We compare the fraction of storm windows that contain an event against the fraction of matched quiet windows that contain an event. A second approach is a permutation test. We hold event times fixed. We slide the set of storm windows randomly across the year, many times, and count how often the random placement produces as many overlaps with earthquakes as the real placement does. This guards against seasonal reporting biases and preserves any slow drift in the catalogue. Because events are rare, we also need patience. A single year will not tell us much. A decade might begin to. That is acceptable. The point of the exercise is not to make day trading decisions based on space weather. It is to test a physical idea. In the meantime, the null result is itself informative. If 10 years of triggers produce no excess overlaps in conductive corridors compared with matched quiet windows, then the claim has hit a wall in the very environment that should make it easiest to see. If a small excess appears, it must survive checks for catalogue stability. Did network sensitivity change during the period? Did a new station arrive that made small events visible in one county, but not another? Did an industrial activity begin or end? These questions are not bureaucratic. They guard against painting noise as pattern. There is a design choice to consider. Should we analyze many intraplate regions at once to gain power, or should we focus on one with excellent data and stable instrumentation? Both approaches have merit. A combined analysis can reveal a faint common tilt, yet it may average away geography that matters. A focused analysis can honor local geology, yet it may never accumulate enough events to be decisive. A balanced plan would choose a small set of regions with clean catalogues and different conductivity structures. It would pre-register a common trigger list and windows. It would allow region-specific geology tags. Then it would pool the final score with a method that weights regions by catalogue quality rather than by population or by interest. Communication in quiet regions requires extra care. Residents who rarely feel earthquakes may connect any two unusual events by narrative. A storm that paints aurora over a normally dark town will be remembered. A tremor the next day will be remembered. Our job is to prevent memory from becoming method. That means sharing the plan openly, including the fact that most storm windows will contain no events and that most events will occur during quiet windows. It means explaining that the test looks for a tiny statistical tilt across many windows, not for perfect overlaps. It also means reminding viewers that the largest documented effects of storms in these regions involve technology. Radio and navigation may wobble. Power systems may see extra current. The ground remains governed by its own long clocks. There is a deeper reason to run the intraplate test well. It teaches general habits of clarity under low signal. The same techniques apply when we test for other subtle couplings in Earth systems. Matching windows, honoring geology, preserving catalogues, and using permutation, thought experiments make claims not only stronger, but simpler to judge. A yes that survives those gates is worth hearing. A no that arrives from them is worth hearing as well, because it closes a door cleanly and lets curiosity move to tracks where the physics points more directly. Our through line stays in view. Known, interiors are quiet yet complex, which makes them a fair stage for subtle tests. Known, technology in these regions responds to storms every time, which helps us time the question. Unknown, whether a whisper from the sky can move a quiet fault, a small step sooner, only along shallow conductive paths, and only within hours to days. Next, we widen the lens to an idea that often rides with big claims, the mirror across the globe. We will weigh the antipodal argument carefully and mark what global stress transfer can and cannot do. Draw a line through Earth from a noisy fault to the point on the far side where the line emerges. That point is the antipode. The idea that a great rupture might echo there has a natural appeal. Waves from a main shock do circle the globe. They cross and recross for hours as low frequency swells. Instruments see them clearly. If waves carry motion, could they also carry enough stress to change the odds of an earthquake on the other side of the world? The answer requires care. It starts with the difference between passing disturbance and lasting change. It then moves through energy budgets and through the patchwork of faults that either accept small pushes or ignore them. Seismic waves radiate outward from a source as body waves that pass through the deep interior and as surface waves that ride the outer shell. Both classes lose energy as they travel. Some loss is geometric because the wavefront grows. Some is anelastic because rocks convert motion into heat. By the time a wave reaches antipodal distances, the motions are gentle compared with those near the source. They are still large enough for seismometers to record. They are rarely large enough to change stress on locked faults by amounts that matter for failure. There are exceptions at volcanoes and hydrothermal systems, where fluids and cracks amplify sensitivity. There, dynamic triggering by passing waves has been observed. The signature is a burst of micro-earthquakes during or shortly after the wave train. It is short-lived and local. It does not produce great earthquakes across oceans. Static stress transfer is another story. When a fault slips, the surrounding crust settles into a new configuration. Stresses change nearby by amounts that are large enough to raise or lower failure probabilities on neighboring patches. This effect decays quickly with distance. It creates aftershock halos and quiet shadows around the rupture, not global echoes. To carry static changes to antipodal distances would require the entire planet to transmit a coherent push without dispersing it. The mantle does not oblige, it allows waves to pass. It does not carry static offsets unchanged to the far side. A minority view holds that the planet can act like a musical instrument at very low frequencies. In this view, the free oscillations excited by a great earthquake might modulate stresses over wide areas for hours or days. Evidence is limited, but one inference is that if such modulation matters at all, it would amplify only sites that are already delicately poised and that contain fluids or other weak materials. The prediction would then be a small and transient rise in very small earthquakes at selected depths, not a surge of large events in a fixed antipodal window. Most catalogues do not show such patterns once statistical controls are applied. There is also an electrical variant of the antipodal idea. It suggests that electromagnetic changes launched by a great rupture could travel through the mantle and core and influence distant faults by changing pore pressures or by altering the electrical state of clays. The physics here is even more constrained. Conductivity in the deep crust and upper mantle is low except along certain belts that carry brines or graphite. The energy available from any electrical source tied to a rupture is small compared with the steady power in the global electric circuit and with the disturbances that storms introduce from above. A distant fault would not notice the difference unless a rare deep conductor created an efficient path and the target fault was both shallow and wet. These conditions are not generally met at antipodal points. The cleanest way to test the antipodal claim is to ask for a pattern that honors geometry, timing, and mechanism together. Geometry would require a concentration of triggered events near antipodes of recent large ruptures, rather than scatter across broad belts. Timing would require a window that opens as soon as the wave train arrives, and that closes as the waves and any oscillations die away. Mechanism would require a preference for environments known to respond to dynamic stresses, such as geothermal fields and volcanic flanks. When researchers apply these filters, the signal weakens. Bursts of small events do occur near volcanoes during the passage of long-period waves. They also occur in many other places, unrelated to antipodal points. Large events do not cluster at antipodes beyond what random chance would deliver in a busy catalogue. Energy accounting keeps the discussion grounded. A great earthquake releases energy, measured on scales that are huge to us and small to the planet. The fraction that reaches the far side as organized stress change is tiny. By contrast, local processes near the antipode are always working. Fluids rise and fall, small faults creep, seasonal loads shift. Those local processes are the background against which any global whisper would have to shout. They tend to win the competition for attention because they operate where it matters, which is at the fault itself. There is still value in the antipodal question even if the answer is modest. It forces us to practice the habit of matching cause and effect on maps and clocks that are large. It reminds us that global wave trains can start local processes in sensitive places, even if they do not trigger large, distant earthquakes. It also keeps the conversation about global stress transfer honest. The true long reach of a great rupture is through static changes on neighboring faults and through changed loading on plates and slabs that share boundaries. These routes work over hundreds of kilometers and over months to years. They help explain why big earthquakes sometimes arrive in pairs along the same system. They do not require a line drawn through the center of the Earth. For our story, the antipodal discussion plays a second role. It helps compare claims. If even the mechanical handshake of a great earthquake with the rest of the planet cannot produce reliable large effects at the far side, then any claim that a space weather perturbation could do so should face an even higher bar. The space-to-stone path is longer and weaker than the stone-to-stone path. The right conclusion is not that the planet is immune to everything. It is that scale and proximity rule. Small pushes work in small neighborhoods. Large pushes work in large neighborhoods. Cross-planet leaps belong to poetry, not to forecasts. Our through-line holds. Known, waves from a main shock can tickle sensitive systems for hours. Known, static stress jumps fade with distance and create local aftershock patterns. Unknown, whether a rare and narrow set of conditions could make distant small responses more likely for a short time. Either way, antipodal drama is not the stage for claims about great earthquakes. Next, we turn from global geometry to human geometry. Communication shapes how people feel during stormy weeks. Clear language can reduce fear without lowering curiosity. That is part of the work too. In a stormy week, the sky glows, power operators post watch notes, and social feeds fill with images that invite awe and anxiety at the same time. Communication is the hinge that can swing either way. With a few careless words, a narrator can turn curiosity into dread. With a few careful choices, the same narrator can keep attention high and fear low while honoring the facts. The first rule is to separate what is certain from what is being tested. The certain part is that the sun and the solar wind can disturb our magnetosphere and ionosphere. These disturbances can affect auroras, radio, navigation, satellites, and long conductors on the ground. The tested part is whether any of this nudges faults that are already near failure. When we speak, we should put the certain part first, put the tested part in a smaller frame, and state clearly that the latter is a research question with no operational use today. The second rule is to give audiences clocks that belong to the physics. Minutes to hours for ionospheric currents, hours to a small number of days for any proposed shallow coupling through fluids. Weeks and months for aftershock decay that follows a great rupture. When an event happens, attach it to the right clock. An aurora tonight is a minute-scale response. A pipeline potential change today is an hours-scale response. An aftershock cluster next month belongs to the long tail of crustal relaxation. This habit prevents the drift that occurs when a narrator stitches together a storm, a mid-sized earthquake 2 weeks later, and an unrelated social crisis. Clocks cut spurious lines before they harden into myths. The third rule is to show the instruments. Trust grows when viewers can see the sources that matter. Upstream monitors that record the solar wind, ground magnetometers that show field changes, TEC maps that visualize ionospheric electron content, seismic networks that time and locate events. When you display these traces, explain what counts as a real change in each. A rising KP index means stronger magnetic disturbance at high latitudes. A southward magnetic field near Earth raises coupling potential. A sudden disruption in radio suggests enhanced ionospheric gradients. A spiky catalogue after a great event is normal aftershock behavior. The instruments become the characters that carry the truth of the story. They also teach audiences how to verify claims for themselves long after the film ends. The fourth rule is to state what will not be said. No predictions of specific earthquakes. No confident claims that a storm will trigger ground failure. No implication that planetary alignments steer the Sunday. Say why these are off limits. The reasons are not political, they are scientific. Tectonic stress dominates fault failure. Planetary geometry is a weak lever for solar magnetic fields. Aftershocks follow laws that outmuscle most small pushes. When viewers hear that some doors are closed for good reasons, they are more likely to walk through the open ones with you. The fifth rule is to use scale wisely. When the coma of a comet is compared with the Sun, say that the coma is a vast yet incredibly tenuous cloud. When a grid feels a storm, say that the induced currents are slow and that they ride on top of the alternating flow. When an earthquake is described, say that its energy comes from years of plate motion and that no near-Earth phenomenon provides an energy source of that size. Scale is a compass that keeps the story pointed toward the real terrain. Small currents can cause trouble in electronics. Giant fault blocks move under pressures that dwarf any surface electrical disturbance. Both statements can be true without contradiction. The sixth rule is to place uncertainty on the table without apology. One sentence can do a great deal of work here. It remains uncertain whether any electromagnetic weather can nudge faults that are already near failure, and if it does, the effect would be small, selective, and hard to detect. Follow this with what would change your mind. A pre-registered test that shows a modest rate increase in line, hours to days after specific solar wind conditions, limited to conductive corridors, and to periods when seismicity is already elevated for local reasons, and that survives matched quiet window checks. This is not hedging, it is a promise about standards. The seventh rule is to offer practical advice that matches the front lines. During a storm, viewers can expect possible issues with radio, precise navigation, and satellite services. Power companies may take protective steps. Airlines may reroute near the poles. Amateur sky watchers can look for aurora at unusual latitudes if forecasts support it. For earthquakes, the advice is the same in every season. Prepare for hazards based on local maps. Secure heavy furniture. Know how to drop, cover, and hold on. Keep supplies ready. None of this is tied to a space weather watch. All of it is useful. The eighth rule is to honor wonder without using fear as a tool. A vivid tail disconnection in a comet is a magnetic story written in blue. A sudden brightening of the aurora is a current map across the sky. Show these as living evidence of how energy moves through space. Let viewers feel the mystery of a planet wrapped in invisible lines that catch charged particles like a net. Invite them to watch indices update in real time during a storm. Then tell them that the crust is largely indifferent to these dances, which makes the survival of mountains and coastlines more impressive, not less. The ninth rule is to think out loud about method. When a headline week presents a tempting overlap between a storm and a ground event, walk the audience through the checklists. Ask whether the aftershock model already explains the local rise in activity. Ask whether the upstream field and density fit any pre-registered trigger class. Ask whether the region sits atop a conductive belt. Ask whether the same rise appears in matched quiet windows. Do this briefly and clearly, then give the answer. Model explains it. Trigger class does not apply. Geology is not favorable. Quiet windows show similar counts. Curiosity satisfied. No claim needed. The 10th rule is to close loops. If you ever announce that researchers are watching specific windows during a storm as a natural experiment, return later and report what was found. Say that the windows passed without tilt, or that a faint hint appeared and is being checked by independent teams. Silence after a tease breeds rumor. Closing the loop breeds trust. Our through line remains steady. Communication is not decoration, it is part of the experiment. When we name the known, label the unknown, and keep scale in view, the public can stare at a sky alive with plasma and feel both safe and moved. Next, we take that same discipline into the editing room. Pacing and structure decide whether a complex story feels clear. There is a craft to building sequences that hold tension while keeping meaning intact. The edit is where science turns into story. A camera can gather beauty, and a notebook can hold facts, yet the rhythm between them is what keeps an audience from drifting away. Pacing is not decoration. It is comprehension delivered on time. Structure is not a cage. It is a set of rails that carry viewers through turns without whiplash. In a film that asks people to hold plasma physics in one hand and earthquake statistics in the other, the edit becomes the quiet engine that makes both feel simple at the moment they appear. Begin with cadence. Alternate short beats that pose a question with longer beats that answer it. Questions should be plain and specific. Why did that comet tail break? Could a storm in space change anything on the ground? Answers should be clear and visual. Show the upstream magnetic field turning south. Show the ion tail snapping in a telescopic frame. Show a grid control room display ticking upward with alarms. Then pause. Let a line of narration remind us that faults obey tectonic clocks and that most ground stories end before the mantle begins. The pause is not empty. It is a reset that makes space for the next idea to land. Use an A and B braid to balance emotion and analysis. The A braid is the storyteller. It brings images, voices, and breath. It moves through the aurora, through a city street at night, through a researcher's face lit by a monitor. The B braid is the analyst. It brings models, diagrams, and the plain language of mechanism. Cut from a family staring at green skies to the plot that shows the solar wind turning. Cut from a road crew watching a pipeline station to a diagram of induced fields in layered rock. Each cut closes a loop. Each loop earns permission to move forward. Give viewers anchors that repeat. Return to the same three instruments whenever the story grows complex. The upstream monitor that reads wind and field. The ground magnetometer that records the swing at the surface. The seismogram that prints the steady heartbeat of local ground motion. These anchors are the cast. When they recur in the same order, the audience learns unconsciously that we are about to test a claim. The order becomes a gentle ritual. Measure the wind, watch the field, check the ground, speak the conclusion plainly. Sequence the film in arcs that climb, level, and climb again. A first climb uses comets to teach the invisible river. A level path explains coupling into grids and pipes. A second climb explores the small push problem and the timing windows that could prove or disprove a link. A level path returns to communication and preparation. A third climb offers the beauty of overlap when many comets draw the same wind at once. Close with a wide view that places our planet inside a living heliosphere, while reminding us that bedrock keeps its own counsel. These climbs keep tension alive without leaning on threat. They replace alarms with curiosity and with the pleasure of prediction tested against reality. Control the density of terms. Introduce one new idea per paragraph in voice, not 3. Define each term with a picture, instead of a subordinate clause. Show a bow shock as a bright arc upstream of a comet. Say it is the line where pressures balance. Show a conductivity map as blue basins and brown shields. Say blue carries currents more easily. The human mind loves names when a picture already holds the concept. It resists names that arrive before an image has settled. Edit to honor this order. Image first, name next, application last. Mark the known and the unknown with a visual grammar. When the script states a verified link, place a solid white caption on the bottom left and a green dot on a small timeline icon. When the script enters speculation, use a hollow caption and a yellow dot that blinks slowly. When the test fails, let the dot turn grey as the narrator says, "Why?" This grammar makes the philosophy of the film visible. It shows that skepticism is not a mood. It is a method that anyone can learn to read. Trim numbers to those that teach scale. Keep one or two that anchor memory. A comet coma that spans hundreds of thousands of kilometers is compelling when the next shot places Earth as a tiny circle inside that bubble. A grid event becomes real when a single transformer temperature rises by a few degrees in a few minutes, while a control room decides to reroute power. A seismic decline becomes intuitive when a scatter of aftershocks on a time plot thins from a storm of dots to a snow flurry. Do not bury viewers under dates and indices. Give them one per scene and repeat it once in a later scene to reinforce learning. Preserve doubt without breaking trust. When the film proposes a test, insert a title card that says pre-registered window, followed by a clock that opens and closes. After the window ends, return to the same card and write result under it with either no tilt detected or small tilt detected, checking controls. The audience learns that the film keeps promises. Even a null result feels like a win because it closes a loop the film itself created. Use sound as structure. A low, steady pulse can mark the magnetosphere when the wind couples strongly. A thin bell can mark the moment an ion tail snaps. Silence can follow any claim that sits on speculation. That silence is a signal to breathe and to remember that the next shots must justify returning to music. Over time, the sound design becomes a companion that tells viewers how to feel without telling them what to think. Edit out any sentence that treats mystery as menace. Replace it with a sentence that treats mystery as a chance to learn. The sky can be intense and still be safe. The ground can be restless and still be governed by rules we understand well. The film earns its wonder by refusing to exaggerate. That restraint turns out to be the most dramatic choice available, because it lets the audience relax into a trust that is rare. Close each section with a forward pull that is honest. Ask a question that the next section really answers. What does a storm do to a transformer core? The next scene shows it. How would a genuine nudge appear in a quiet catalogue? The next scene tests it. Could many comets in one season let us map the wind as if we owned a whole fleet of probes? The next scene draws that map in light. The rhythm becomes predictable in the best way. The mind leans ahead because it believes the film will keep its word. Our through line remains visible even in the cut. Known, how energy moves from a star to a sky and into wires. Known, how faults keep time with plates and with their own history. Unknown, whether a slim and selective window hides a whisper of coupling that matters. The edit carries this triad like a melody that returns. It guides eyes and ears without tricks. It lets viewers feel that they have learned something hard because the film made the learning easy. If a small and selective nudge exists, it will not be found by a single lab guarding a secret spreadsheet. It will be found by many eyes watching the same clocks and posting the same rules before the sky changes. Open science is not a slogan here. It is the only practical method for detecting a whisper that hides inside noise. The playbook is simple to state and hard to fake. Declare triggers in advance. Declare timing windows in advance. Declare geography and geology filters in advance. Share the code that turns a solar wind time series into a start bell. Share the code that matches quiet windows. Share the code that scores outcomes and that draws the final plots. If the hint survives in many hands, it might be real. If it fails in many hands, the story moves on gracefully. Start with open inputs. The upstream measurements that matter are already public. Solar wind speed, density, and magnetic field vectors stream from satellites in near real time. Ground magnetometer networks post the field variations at high cadence. Indices that summarize the storm state are updated on schedules that amateurs can follow. Seismic networks publish event times and magnitudes within minutes and archive refined catalogues later. Magnetotelluric surveys and conductivity maps are available for many regions and can be approximated elsewhere by public geology. The raw materials are out in the open. The value comes from recipes that anyone can run. Next comes pre-registration. A short, plain page is enough. Name the satellite data source and the rules that convert it into triggers. For example, a sustained southward magnetic field below a threshold for a minimum duration, or an entry into a low-density, high-speed stream defined by objective cutoffs. Name the timing windows that follow a trigger. For example, the first day after onset, days 2 and 3, and days 4 and 5. Name the geological tags that mark regions where induction should be stronger. For example, coastal sedimentary basins and rift belts with survey evidence for conductors. Name the seismic magnitude threshold that balances completeness and sample size. Name the control design that pairs each storm window with a matched quiet window. Post this page with a date. Invite others to mirror it or to register their own variants with differences explained. Then publish the tools. Shared notebooks that fetch data, apply filters, and produce figures are the backbone. Use clear variable names and comments that connect each step to the physics. One block pulls the solar wind and computes when triggers start and stop. One block ingests ground magnetic variations to provide a local validation that coupling occurred. One block selects the seismic events for each region and magnitude class. One block applies the windows and counts events. Another computes expectations from background rates or from fitted aftershock laws. The last blocks compare storm and quiet windows, run permutation tests, and print summary statistics with uncertainty. The same repository should include instructions for swapping in different regions and for updating catalogs as networks improve. Replication is more than rerunning code. It is running code in places with different noise and different geology. A group near a subduction margin can test aftershock sequences with thousands of events. A group in the interior can test a decade of quiet with only dozens of events. A group with strong coastal conductivity can test where induction should be most visible. A group on crystalline shields can test where induction should be weak. The agreement that matters is not only a p-value, it is a pattern that respects both the physics of coupling and the differences in the ground. Transparency also governs decisions after the fact. If a study promised to watch 3 rotations of a recurring fast stream, it should report after each rotation, even if nothing tilts. If one rotation produces a hint while the next 2 do not, the report should say so and should downgrade the claim. If an unexpected storm class produces a hint that was not in the plan, the report should label it exploratory and should write a new registration for the next season. This rhythm of promise and accounting is the same one that grid operators use when they evaluate procedures after a storm. It turns curiosity into a practice rather than a mood. Open data encourage cross-checks outside the main hypothesis. A user interested in radio and navigation can align the same triggers and windows with total electron content maps to see how the ionosphere behaved. A user interested in pipelines can compare pipeline potential logs with the geoelectric fields implied by ground magnetometers. These side studies keep the space weather part of the story sharp. When the upstream state is ambiguous, or when the ground response is weak, the earthquake analysis should be paused rather than pushed. Seeing the other instruments flat reminds everyone that the silent ground is not being coy. It is simply experiencing a weak storm. There is a human reason to keep the process public. Communities that live with earthquakes already deal with rumor during tense weeks. When a storm adds aurora to the sky, the rumor mill accelerates. A public dashboard that shows the registered windows, the current triggers, the real-time ground magnetic variations, and the running count of earthquakes against expectation can calm that traffic. The dashboard does not predict, it teaches. The effect of a storm on grids and on satellites is visible. The absence of a tilt in the quake windows is also visible. If a small hint appears, the dashboard can mark it as tentative and point to the plan for independent checks. The same page can carry practical guidance about power, communications, and safety that does not change from week to week. The open playbook has room for negative results that still generate knowledge. Suppose several groups follow the same rules across 2 years that include many storms and at least one major aftershock sequence. Suppose the pooled result shows no tilt in any window beyond what matched quiet windows deliver. That outcome does not waste the audience's attention. It strengthens confidence in what space weather reliably affects, and it frees analysts to focus on engineering protection and on aurora science. The code and the habits can be reused for other small push questions in geoscience, which makes the work portable and valuable beyond this specific debate. Open does not mean sloppy. It means stricter. Pre-registration forces a plan to face the wrong storms as well as the right ones. Shared code forces methods to pass the test of clarity. Public dashboards force communication to match clocks and scales. Each of these pressures is a discipline. Each shields the story from the temptation to let coincidence write the script. Our through line continues without strain. Known, the relevant data streams are public and abundant. Known, replication across places and seasons is the cure for coincidence. Unknown, whether any small and selective tilt hides inside the windows we can all watch together. Next, we point the lens back to the sky and to the visitor that helped us build this laboratory in the first place. The comet is a messenger of both physics and perspective. It will leave soon. What remains is what we learned by watching it. Every comet is a clock with a bright hand. It sweeps across the sky and reminds us that our region of space is not a void. It is a river with weather and with structure that we can learn to read. When the visitor departs, the gift it leaves is not just a set of images, it is a practice. Watch the wind, watch the field, check the ground, speak clearly about what changes and what does not. That habit is a kind of literacy. It turns a spectacle into a skill that anyone can use when the next sky event arrives. The first part of the gift is scale. A coma the size of a star is a startling phrase, yet that bubble is made of gas so thin that a human breath contains more particles than a stadium full of that material. That contrast teaches balance. Vast does not always mean strong. Small does not always mean weak. The same lesson appears in our power lines. A slow current that would barely flicker a lamp can trouble a transformer core because of how that core is designed. The magnitude that matters is the one that matches the mechanism. Once you see scale through that lens, you stop comparing storms to earthquakes as if they were cousins. You start asking what each system is sensitive to. Electronics care about bias and harmonics. Faults care about shear stress and fluids under pressure. The two worlds do speak to each other, yet they do so through narrow doors and on short clocks. The second part of the gift is patience. Comets do not rush. They brighten, then they fade. Tail kinks appear hours after an upstream turn in the field. Boundary squeezes follow pressure changes with a lag that depends on the outgassing rate. The sky writes in cause and effect with delays that we can measure. That rhythm trains the eye to expect tests rather than anecdotes. When a headline week places a storm near a quake, the habit that the comet teaches is to look for the upstream state, then to look for ground fields, then to place windows on the timeline that make sense. If those checks do not line up, the habit is to let the coincidence go. Wonder remains. Panic recedes. That is a social good as real as any graph. The third part is humility that does not weaken curiosity. An interstellar visitor carries chemistry from elsewhere. Spectra reveal signatures that differ from many local comets. Its coma maps the magnetic field by the way it bends. These facts are thrilling. They are also a reminder that our first stories about strange objects often need revision. We place a candidate mechanism on the table. We mark what it would predict that is different from other ideas. We watch. We change our minds as data arrive. This is how the story about comets themselves grew from omens into physics. The playbook serves us well when we weigh subtle claims that bridge sky and stone. We can enjoy speculation, as long as we label it and give it a fair chance to fail. The fourth part is connection. A comet is a public event. A telescope in a backyard and a space observatory on the far side of Earth can both contribute. Photos from amateurs help trace the evolution of the tail from hour to hour, which can catch features that professional campaigns miss between scheduled exposures. A network of small magnetometers near schools lets students watch the field wiggle when a storm arrives. An open seismic dashboard lets communities see their local ground motion settle after a main shock. These are not separate hobbies, they are notes in a shared score. They build a culture that trusts instruments and learns to read them together. The fifth part is a checklist for future seasons. Keep a short list of upstream triggers. Keep a short list of timing windows. Keep a short list of regions where geology favors induction. Keep a short list of measures that matter for frontline systems. A checklist is not dull. It is freedom from improvisation that blurs memory. During the next storm, the list turns a noisy feed into a few clear questions. Did the field turn south and hold? Did ground stations show rapid changes? Are we inside a pre-registered window? Do grids and pipelines report the usual signatures? The answers guide both narration and action. If the last two answers are no, the story returns to Aurora and to technology without dragging faults into the frame. The sixth part is a better question to carry forward. Instead of asking whether storms cause earthquakes, ask how different parts of Earth couple to electromagnetic weather. The ionosphere responds first. Long conductors on the surface respond next. Shallow porous rocks may respond weakly in special settings, especially where conductive layers and fluids provide a path. Deep locked faults mostly ignore the show because the signal fades long before it reaches them. That map is not a slogan. It is the outline for research that can succeed. It invites studies that link magnetotelluric maps to pipeline logs. It invites forecasts that include regional conductivity when they translate index values into ground fields. It invites careful attempts to detect micro-effects in places where physics says they might appear. It closes the door on claims that ask too much of the path from space to stone. The seventh part is joy. A sky with a living tail can pull a child outdoors at night. An aurora over a lake can make strangers share a field and speak softly. A plot that shows a sudden turn in the magnetic field can move a person who never imagined that invisible lines above a planet could rearrange in minutes. Joy is not separate from rigor. It is the energy source that keeps attention long enough for method to matter. A film that preserves joy while it teaches restraint leaves people more awake, not less. The visitor will fade, the instruments will remain, so will the habits. We will still have upstream monitors to read the wind, ground stations to read the field, and catalogues to read the ground. We will still have engineers who treat forecasts as real. We will still have communities that know what safety looks like in any season. The comet's last and best gift is to make these ordinary things feel vivid. It reveals the world we already live in, a world where a star breathes, where a planet wears a magnetic cloak, and where stone keeps counsel with pressure and time. That is enough wonder for many winters. We have walked a long arc together. The story opened with a restless star, a visitor with a bright breath of gas, and a planet ringed by an invisible shield that sings when the wind arrives. We followed energy from the sun to the magnetosphere, from the magnetosphere to the ionosphere, from the ionosphere to wires and pipes, and from there into the shallow ground. At each step we asked what is known and what is not. We asked how much power moves and how fast it moves. We asked which systems answer every time, and which systems mostly ignore the sky. That compass is how the film earns its final shape. It lets us close with clarity, while leaving room for wonder that does not depend on alarm. Here is the core that stays. Space weather is real, measurable, and often beautiful. It drives currents in the ionosphere. It induces slow currents in long conductors on the surface. It perturbs radio links and satellite paths. It decorates the night with curtains of light that spill toward latitudes that rarely see them. It sometimes knocks on the door of a transformer or a pipeline valve house and asks operators to pay attention. These are not guesses. They are logbook entries and plots on screens, and lessons learned the hard way by teams who now prepare well. That is the territory where the film speaks in the voice of fact. Here is the space that invites careful curiosity. A small and selective nudge might exist for faults that are already near failure, especially in places where shallow conductive pathways and fluids offer an electrical handle on rocks. If such a nudge exists, it would operate on hours to days after specific upstream states. It would prefer regions the geology tags as favorable. It would be modest against the loud script that a great rupture writes for its aftershocks. It would come and go without changing long-term hazard. Proving or rejecting this edge case requires a public playbook, pre-registered timing windows, matched quiet controls, and cross-checks that survive when other groups run the same code on other ground. Here is what the film sets aside: predictions of specific earthquakes, stories that give planetary alignments the steering wheel of the Sunday claims that treat coincidences as plans written in the sky. These do not need to be pushed away with scorn. They need to be set on the correct shelf with a label that says, interesting, idea. No physical path, no supporting pattern. That habit keeps attention where it belongs, on mechanisms that turn energy into effects without leaping across gaps that math and instruments refuse to cross. The comet that helped us frame this season will fade as its ices spend their brief moment in light. What remains is a practice that anyone can keep. Check the upstream wind and field. Check ground magnetic swings. Check the instruments that record the ground beneath your feet. When a storm watch is issued, expect aurora and radio surprises and a little extra hum on long wires. When a large earthquake rattles a margin, expect aftershocks that fall away as the system relaxes. If these two timelines overlap, use the clocks we learned: hours to days for induction, weeks to months for crustal healing. You will find that most overlaps are coincidences that a calm model explains. The few that are not will glow as honest puzzles because the test was written before the sky changed. There is also a quiet promise in this approach. The same discipline that keeps claims modest makes wonder stronger. When the aurora rises, you know why it stands where it stands. When a comet tail snaps, You can imagine the field turning far upstream and racing outward to meet a cloud of ions that show it in blue. When a transformer hums a little louder, you can picture the slow bias that rides on top of the alternating tide. When the ground shakes, you can hold in one breath the patience of plates and the sudden grace of failure at depth. Wonder based on understanding lasts longer than wonder based on fear. It also spreads more easily because it asks no one to suspend judgment. The invitation at the end of this story is simple. Watch with us. Keep the dashboards open during the next storm. Keep the seismic map open after the next main shock. Keep the pre-registered windows pinned where anyone can see them. If a small tilt appears inside those windows, say so, and invite attempts to break it. If nothing appears, say so, and show the instruments that prove the sky was busy anyway. Say it cleanly either way. The reward is trust. The reward is a public that learns to read plots the way sailors once learned to read clouds. The reward is an audience that returns for the next film because the last one kept its word. The world does not require us to choose between mystery and method. It asks us to carry both. A river of charged particles threads the space between planets. The current of culture runs through our rooms as we share images and numbers. The crust carries the load it has carried for ages and only rarely lets go. Between these three currents there are many stories to tell. The only constant should be the compass we carried here. Name what is known. Name what is uncertain. Test the few places where a connection might live. Refuse to sell fear when facts are already astonishing. If you remember one image on the way out, let it be a simple one. A child on a hill watching lights move across a cold sky, while a parent checks a small screen that shows the interplanetary magnetic field turn and a line on the ground that shows the field at home begin to swing. Somewhere far away, a pipeline technician adjusts a control. Somewhere else, a grid operator holds reserve. Somewhere underfoot, stone keeps its counsel. The child hears none of this and feels only awe. Years later, the same child learns the clocks and the channels and finds that awe grows, not shrinks, when the path from light to line to life becomes clear. The film ends where it began, with a promise. We will keep watching together. We will keep asking fair questions. We will keep closing loops in public. The sky will keep offering chances to practice. The ground will keep telling the truth in its slow language. Between them, we will keep finding ways to turn curiosity into understanding without losing the feeling that started it all.